Black holes are areas of space with gravity so strong that nothing, not even light, can escape. Some scientists propose that the core of a black hole might not only destroy matter, but could also create a new universe on the other side. Beyond the event horizon, there might not be an ending, but a transition. Could our entire universe exist inside a black hole? Before we embark on this cosmic journey, drop in the comments below where in the world you're watching from and what time it is there now. Then, settle in and get ready as we delve into this puzzling mystery. At the very centre of a black hole, something extraordinary happens, something that breaks the usual rules of physics. But before anything reaches that central point, there is a boundary, a line that marks a turning point. This boundary is called the event horizon. Most people have at least heard the term. It is the surface that separates the rest of the universe from the unknown inside the black hole. Once anything crosses this line, not even light can escape. But what does that really mean? The event horizon is not a solid wall. You wouldn't collide with it like hitting a barrier or force field. If you were falling into a very large black hole, you might pass through it without noticing anything at all. There would be no flashes of light, no sudden change in pressure or temperature. Crossing it would feel completely ordinary. Yet, the moment you pass this invisible boundary, everything you understand about space and time begins to shift. What makes the event horizon truly strange is not only what happens after something crosses it, but also what it means for the rest of the universe. The event horizon doesn't just hide what is inside a black hole, it prevents any information from escaping. Everything that falls in, light, particles, energy, even the history of objects, is cut off from the outside world. It is not just unreachable. In terms of what we can observe, it is erased. The black hole does not send any hints or signals. Once something passes the event horizon, it is gone from the observable universe. This is where physics begins to feel philosophical. The laws of physics are based on the principle that information is never truly lost. Even when a physical object is destroyed, for example, when a log burns in a fire, the information about its atoms and energy does not disappear. It only changes form. Black holes, however, seem to challenge this idea. From the outside, all we see is a black hole's gravity pulling in more mass. We do not know what falls in or how. The details are hidden behind the event horizon. This puzzle has baffled scientists for decades. The event horizon also warps time. From an outside perspective, anything falling into a black hole appears to slow down as it approaches the edge. It seems to freeze at the surface. A spaceship falling in would look like it is hovering there forever, slowly fading from view in red light before vanishing completely. But for those on the ship, time flows normally. They pass through the horizon and continue toward the center, unaware that to an outside observer they have stopped moving at all. Two completely different experiences of time exist simultaneously, one for the inside and one for the outside. This split creates a deep mystery. Observers outside a black hole cannot access any information about what is happening on the other side of the event horizon. The usual rules of reality, space, time, cause, and effect, do not function in the same way. From this perspective, the event horizon represents the edge of what can be known. From the point of view of the universe as a whole, the event horizon has profound consequences. Physics relies on the ability to predict the future from the present. If you know the position and motion of every particle, you can calculate what will happen next. But anything hidden behind an event horizon is removed from these calculations. This means the rest of the universe is influenced by something it can never see or measure. If parts of the universe are permanently inaccessible, how much can we truly know? Is physics about describing reality, or only describing what can be observed? The event horizon forces us to confront that distinction. It shows that even fundamental ideas like space and time depend on location and motion. There may never be a single, complete story of the universe, only perspectives stitched together from limited views. Some scientists propose that everything inside a black hole might be encoded on the event horizon itself. This is the idea behind the holographic principle. It suggests that the event horizon could store all the information about the black hole's interior, like a two-dimensional blueprint projecting a three-dimensional reality. If true, the event horizon is not just a boundary. It could act as a cosmic storage device, holding patterns of information about everything that ever fell into the black hole rather than the objects themselves. This radical idea is still being studied, but it may help answer one of physics' greatest questions: whether information is ever truly lost. No one has seen an event horizon directly, yet we have observed evidence of its presence. For example, the Event Horizon Telescope captured an image of a black hole's shadow in the year 2019. That shadow was not the event horizon itself, but it revealed where the horizon must be. The black hole's gravity carved out the absence of light, creating a ghostly outline, not defined by what exists inside, but by what cannot escape. Like the horizon on Earth, the event horizon marks the edge of what can be seen, but not necessarily the edge of what exists. Beyond it may lie realms we will never reach, never measure, and perhaps never understand. According to Albert Einstein's groundbreaking theory of general relativity, gravity is not a force in the way we usually think about it, like the pull that draws objects toward Earth. Instead, gravity is a manifestation of how mass and energy shape the very fabric of the universe, which physicists call space-time. Imagine space-time as a flexible, invisible stage where all cosmic events unfold. When you place an object with mass on this stage, it bends and curves the fabric around it. The more mass an object has, and the more it is packed into a small area, the stronger this curvature becomes. This bending of space-time is what produces the effect we perceive as gravity. On Earth, this curvature is relatively mild, just enough to keep us anchored to the ground and to slightly bend light passing near massive objects. The effect is subtle but measurable. It even requires engineers to adjust the clocks in Global Positioning System satellites to account for this tiny warping of space-time, or else the GPS readings would quickly drift out of sync. However, in the case of a black hole, the bending of space-time becomes extreme, almost incomprehensible. Black holes are regions where mass has been compressed into an extraordinarily small volume, creating a gravitational pull so intense that the stage itself curves back on itself in a way that defies ordinary understanding. At the edge of a black hole lies a boundary known as the event horizon. This boundary marks the point of no return. Once anything crosses it, from dust particles to light itself, escape is impossible. Here, the curvature of space becomes so steep that time, from the perspective of an outside observer, appears to slow down dramatically. Right at the event horizon, time seems to stop entirely, frozen in place by the overwhelming gravity. Before reaching this edge, another curious phenomenon occurs: the bending of light. Around Earth, light bends only slightly due to our planet's gravity, a tiny effect detectable only with sensitive instruments. Around a black hole, however, this bending becomes so severe that light can orbit the black hole in complete circles. If you were to shine a flashlight sideways at exactly the right distance from a black hole, the light beam could circle the black hole repeatedly before eventually being pulled in. This special orbit is called the photon sphere, and it is a unique region where light becomes trapped, forced to follow a circular path by the extreme curvature of space-time. The photon sphere represents a delicate and unstable balance. Any slight change in direction, and the light would either escape or be swallowed by the black hole. It is one of the most extraordinary consequences of gravity as described by general relativity. Moving deeper toward the black hole, the behavior of space-time becomes even stranger. Inside the event horizon, space and time no longer act as separate dimensions in the way we experience them in daily life. Instead, they begin to swap roles. For an object falling into the black hole, moving forward in time becomes indistinguishable from moving inward toward the center. In other words, no matter what the object does, it is compelled to move toward the singularity at the core. Attempting to turn around and escape is mathematically equivalent to trying to reverse the flow of time, which is impossible. This is why nothing can escape once it passes the event horizon. The geometry of space-time itself dictates a single direction of motion, inward. Einstein's equations allow for even more unusual possibilities hidden within black holes. One of these is called a closed time-like curve. In simple terms, this is a path through space-time that loops back on itself, allowing an object following that path to eventually return to the point where it started, possibly even arriving at an earlier moment in time. These closed loops appear in certain mathematical solutions to Einstein's equations, particularly those describing rotating black holes, known as Kerr black holes. Unlike non-rotating black holes, which are perfectly spherical, Kerr black holes spin, dragging the surrounding space-time along with them. This spinning action not only twists the matter that falls into the black hole, but also twists space-time itself. Near the core of a rapidly spinning black hole, the twisting can become so intense that these closed loops, or time-like curves, could theoretically exist. Following one of these paths might allow something inside the black hole to trace a route that eventually leads it back to its own past. The remarkable feature of these loops is that they arise naturally from the geometry created by the black hole. They do not require the construction of a separate time machine. Instead, they are an emergent property of space-time under extreme gravitational conditions. Whether closed time-like curves can actually exist in reality is uncertain. Physicists are still debating if these loops are merely mathematical curiosities or if they could occur in the real universe. There may be fundamental laws of physics that prevent such curves from forming, or perhaps the universe itself is too short-lived for them to have any practical effect. Even so, the fact that Einstein's equations allow these possibilities demonstrates just how flexible and strange spacetime can become under the influence of extreme gravity. Another intriguing idea emerging from the mathematics of black holes is the concept of folded or highly distorted space. According to some theories, the interior of a black hole might not be a single point of infinite density, known as a singularity, as once thought. Instead, it could be more complex, potentially forming a tunnel or passageway through space and time. Such a tunnel is called a wormhole, and it represents a solution to Einstein's equations in which two separate regions of spacetime are connected by a narrow throat. In principle, an object passing through a wormhole could exit in a completely different location, or even at a different time. These wormholes are not stable under normal circumstances. They would collapse instantly unless held open by a form of matter with unusual properties, often referred to as exotic matter. Nonetheless, the mathematical possibility of such tunnels suggests that the interior of a black hole could be far stranger than the simple concept of a singular point would imply. In some versions of rotating or electrically charged black holes, the inner region may not collapse to a point but instead form a bridge leading elsewhere, potentially allowing passage through the black hole rather than destruction. This idea remains highly speculative, but it underscores the remarkable potential for spacetime to adopt configurations that are completely unlike anything we encounter outside extreme gravitational fields. The effects of black holes extend beyond strange loops and tunnels. Another phenomenon known as frame dragging arises near rotating black holes. When a massive object spins, it pulls the spacetime around it along with its motion. Near a rapidly spinning black hole, this dragging becomes so strong that it forces everything nearby to rotate in the same direction, regardless of whether the objects are moving on their own or trying to hover in place. The very fabric of space is literally twisting, and traditional directions such as up, down, left, or right begin to lose their conventional meaning. Time itself can take unexpected directions, flowing in ways that seem counterintuitive compared to everyday experience. As one moves closer to the center of the black hole, the familiar rules of geometry and motion start to dissolve. Distances between points become difficult to define, and time becomes so entangled with space that the ordinary notions of motion and position break down completely. The logical consequences of Einstein's equations stretched to their extremes paint a universe within black holes that is almost surreal. Geometry, the framework of spacetime, becomes a dynamic and often unpredictable entity. Near a black hole, the stage on which the universe plays out its events warps into loops, spirals, and folds. Straight lines no longer remain straight. Paths through space can curve back on themselves. Time, which outside a black hole always flows in one direction, may form cycles or loops under certain conditions. The event horizon marks the edge of what can be observed or reached, but it is not the edge of what is mathematically possible. Beyond it lies a domain where geometry itself can behave in extraordinary ways. Inside this hidden world, conventional understanding of the universe no longer applies. The deep interior of a black hole could be a place where space is folded upon itself in ways that allow shortcuts or bridges, where the flow of time is radically different from what we experience, and where the fundamental structure of reality contorts under extreme conditions. The spinning core of a Kerr black hole may even permit paths that loop back to the past, at least according to the equations. The innermost regions might contain tunnels connecting distant points of space, or even different moments in time. These possibilities highlight just how far general relativity stretches our concepts of what is possible, revealing that gravity is not just a simple pull, but a force that can reshape the universe at its most fundamental level. Even if no human or particle could ever survive entering such a place, the mathematics allows for scenarios that are astonishing to imagine. Black holes challenge our deepest intuitions about space, time, and motion. They demonstrate that the universe is not constrained to behave like the world we see every day. Instead, under the influence of immense mass and energy, the universe can form structures so extreme that time can bend, light can orbit indefinitely, space can fold into hidden bridges, and events could, theoretically, repeat in endless loops. In this sense, black holes are laboratories for the laws of physics pushed to their absolute limits. They are not merely endpoints for matter and energy. They are regions where space-time itself becomes a dynamic, flexible, and almost fantastical entity. The photon sphere, the event horizon, the twisting of space-time, frame dragging, closed time-like curves, wormholes, and all the other extreme geometrical phenomena predicted inside black holes are consequences of Einstein's elegant equations. The term singularity often makes people think of a tiny invisible dot tucked away at the very centre of a black hole, a spot where everything that falls in is crushed into a state of total collapse. The common image is of something with no size at all, yet somehow carrying infinite density, a place where gravity grows so strong that space and time themselves seem to break down. It is a dramatic picture, one that captures the imagination and even feels terrifying. Yet, despite how compelling it is, this traditional image of the singularity might not be correct. In truth, the singularity may not exist as an actual physical point in space at all. Instead, it might be a sign, an indication that our current understanding of physics and the mathematics we use to describe the universe has reached its limits. In physics, whenever calculations produce infinity, it is usually a sign that something has gone wrong, not a discovery of a real, infinitely large or dense object. Infinity is not a number that can actually be reached. Rather, it is more like a warning light on a dashboard, flashing to indicate that a theory is being pushed beyond the range where it works. In Einstein's theory of general relativity, which describes how gravity works on large scales, the singularity emerges as a place where space-time curves so sharply that it can no longer be described using our usual formulas. Gravity continues to increase without limit, and the equations we normally rely on to describe motion, energy, or even light itself stop giving meaningful answers. Instead of numbers, the math begins to produce nonsense. According to this theory, this breakdown occurs at the very centre of a black hole, in the spot where all the matter that has fallen into it is thought to collapse. But here lies an important complication. General relativity is a theory that deals with large-scale structures like stars, planets, and galaxies. It does not account for the strange and tiny rules that govern the behaviour of very small objects, such as atoms, electrons, or subatomic particles. Those rules fall under the domain of quantum mechanics. The problem arises when we face situations like the centres of black holes, where both gravity and quantum effects are extremely strong. At that point, we cannot simply ignore one theory in favour of the other. Yet today, physics has no single framework that fully unites general relativity and quantum mechanics. The result is that when we speak of a singularity, we're really talking about a location where our current understanding fails. It is not a physical dot in space, but more like a giant question mark in our knowledge. This raises many difficult questions. What actually happens to the matter and energy that falls into a black hole? Do they shrink endlessly? Do they disappear entirely? Could they somehow emerge in another part of the universe, or even in another universe altogether? Our present theories do not offer clear answers, not because the answers do not exist, but because we simply lack the mathematical tools and physical models to discover them. Some physicists speculate that once we develop a complete theory of quantum gravity, a theory that combines the bending of space from general relativity with the uncertainty and probabilistic nature of particles from quantum mechanics, the singularity might vanish from our equations. In such a theory, gravity might not be a smooth, continuous curve as in Einstein's model. Instead, it could be made up of tiny, discrete units, like the individual pixels of a digital screen. Space and time themselves could have a smallest possible scale, a kind of quantum granularity. If this is true, then the singularity may never actually form. What appears as a point of infinite collapse could instead be a complex quantum structure that obeys new rules we do not yet fully understand. There are already hints that this might be the case. One example is a field of study called loop quantum gravity, which proposes that space is composed of incredibly small loops. In this framework, when matter collapses under the influence of gravity, it does not condense into an actual singularity. The loops create a kind of pressure that resists further collapse, potentially producing a bounce rather than an infinite density. Instead of a bottomless pit, there may be a mechanism that halts the collapse and redirects it in a new form. Another approach comes from string theory, which imagines that all matter is made of tiny vibrating strings that are far smaller than atoms. Under extreme conditions, such as those near a black hole's center, the behavior of these strings could change dramatically. New types of particles or even hidden dimensions could emerge, meaning that what we interpret as a singularity is not a breakdown of physics at all, but rather a place where new physical laws dominate. Despite differences in their approaches, these theories share one crucial idea. The singularity should not be treated as a final truth about the universe, but rather as a marker showing the limits of our current knowledge. It is a point where our map of the cosmos runs out. There are additional reasons to doubt that singularities are physical objects. For instance, the equations of general relativity predict a singularity at the very beginning of the universe, at the moment of the Big Bang. According to these equations, all matter in the cosmos was compressed into a single, infinitely dense point. However, most scientists today believe that this early state was not a true singularity either. Instead, it was an extremely dense, hot, and chaotic condition, a moment when quantum effects were crucial. By analogy, black hole singularities might also represent a situation we do not yet fully understand rather than actual physical points. Studying black holes presents enormous challenges precisely because we cannot directly observe what is happening at their centers. We can only rely on theoretical models, indirect clues from mathematical equations, and patterns that emerge from what we can detect around the black hole, such as the behavior of light, matter, and gravitational waves. The singularity, therefore, remains entirely beyond our observational reach, making it one of the most urgent problems in theoretical physics. If our current models produce infinities, that is a clear sign that we need new models, new rules, and new mathematics. Physics is not simply about describing what we can see. It is about uncovering simple and universal laws that explain why things behave the way they do. There is also a deeper, more philosophical problem associated with the idea of a singularity. If a singularity represents a point where time itself ends, what happens to the very concepts of cause and effect or the passage of time? Does time simply stop, or does it transform into something else entirely? Our usual ways of understanding the universe, based on cause and effect and the linear flow of time, break down. In this sense, the singularity is not just a physical puzzle, it is a challenge to logic itself. It forces us to confront whether the universe is always orderly and understandable, or whether there exist extreme corners of reality where even reason fails. Despite these difficulties, scientists continue to explore these frontiers. Observational breakthroughs are already providing new insights. The detection of gravitational waves, which are ripples in space-time caused by the collision of black holes, has opened an entirely new window into extreme gravity. Direct imaging of black hole shadows, like the famous image of the black hole at the center of galaxy Messier 59 in the year 2019, has begun to reveal the shapes and behaviors of regions close to the event horizon. Advances in telescope technology, computational power and theoretical models may one day allow us to piece together a clearer picture of what happens at the very heart of black holes. While the singularity remains an enigma today, it also represents an invitation, an opportunity to extend our understanding of the universe into realms that remain mysterious, pushing the boundaries of both mathematics and physics. From a distance, black holes appear deceptively simple. They all seem like dark, empty voids, regions in space where gravity reigns supreme, swallowing everything nearby, even light. Yet, as with stars, which come in a breathtaking variety of sizes and types, black holes may also hide a remarkable diversity within. What we see from the outside, a dark sphere surrounded by swirling gas, sometimes bright with radiation, is just the surface. The interiors of black holes, the parts we cannot directly observe, may tell very different stories depending on their size, origin, and physical properties. One of the clearest distinctions among black holes is their size. Some are only a few times heavier than our Sun, modest in comparison to the vast scales of the universe. These are known as stellar mass black holes. They form when a star reaches the end of its life and explodes in a supernova. A typical stellar mass black hole has a mass between 5 and 50 times that of the Sun. Their boundaries, known as event horizons, the point of no return, are only a few tens of kilometers wide, small on cosmic scales but deadly close up. Gravity at these boundaries is so intense that if someone were to fall in, the difference in gravitational pull between their feet and their head would stretch them out like a piece of taffy. This dramatic stretching is known as spaghettification, and in smaller black holes it happens almost immediately, long before reaching the centre. In contrast, supermassive black holes are giants, millions or even billions of times heavier than the Sun. These leviathans reside at the hearts of galaxies, including our own Milky Way. Their event horizons are immense, often large enough to enclose entire solar systems. Despite their massive gravity, the pull near the horizon can feel surprisingly gentle. If someone were to fall into a supermassive black hole, the difference in force between their head and feet would be minimal. They could drift across the horizon without any noticeable stretching, without pain or sudden force. It is only much deeper, closer to the centre, that gravity intensifies dramatically. This contrast in experience between stellar and supermassive black holes hints at profound internal differences. The interiors of supermassive black holes may be structured in ways that allow matter more time before collapsing, or that permit complex interactions unseen in smaller black holes. Some theoretical models suggest that inside these giants, entirely new forms of physics could emerge, phenomena that do not occur anywhere else in the universe. Beyond size, the origins of black holes may influence their interiors. Primordial black holes, for instance, are tiny ancient objects that could have formed shortly after the Big Bang, long before stars or galaxies existed. These black holes were not born from dying stars, but from dense regions of matter in the early universe collapsing under their own gravity. They might range in mass from something as small as an asteroid to something heavier than the Moon. Unlike stellar mass or supermassive black holes, primordial black holes could be dominated by quantum effects rather than classical gravity. Their formation would be a purely geometric phenomenon, space folding in on itself without the heat, light, or nuclear processes that mark stellar evolution. Some of these black holes may have already evaporated due to Hawking radiation, the slow release of energy that causes black holes to shrink over time. Others might still exist today, scattered across the cosmos, potentially even contributing to dark matter. Inside, they may contain bizarre quantum structures, loops of energy, fluctuating fields, or forms of matter unlike anything observed elsewhere. Black holes may also differ depending on whether they spin or carry electric charge. The simplest kind, known as a Schwarzschild black hole, is non-rotating and uncharged. Its interior is thought to contain a singularity, a point where density and curvature reach infinity. Yet, most real black holes are more complex. Rotating black holes, called Kerr black holes, and charged black holes, called Reissner-Nordström black holes, have far more intricate internal structures. A spinning black hole may possess a ring-shaped singularity, a loop where space itself becomes undefined. In some mathematical models, this ring could lead to other regions of space or even alternate universes. However, the internal structure of spinning black holes may be unstable. As matter falls in and spins accumulate, the geometry can twist and contort, creating chaos inside. Tiny fluctuations may amplify, breaking down any smooth, predictable interior. Instead of calm, tunnel-like structures, the interiors may be turbulent seas of warped space, where no trajectory is stable, and no prediction is certain. Charged black holes offer yet another twist. Theoretical calculations suggest that they could feature two horizons, an outer and an inner one, separated by a region where space and time behave strangely. In this region, time and space may switch roles, allowing matter to move between horizons without immediately encountering the singularity. In practice, however, charge may not last long in the real universe. Black holes could neutralize quickly, causing these unusual internal features to collapse or never fully form. These examples illustrate a key point. The interior of a black hole is not a simple, uniform story. It can vary depending on formation history, mass, rotation, charge, the nature of infalling matter and other factors. two black holes with the same mass may hide radically different interiors, shaped by distinct cosmic histories. This complexity becomes even more intriguing when black holes collide. Observatories such as LIGO have confirmed that black holes merge, sending ripples across space-time known as gravitational waves. These waves reveal the motion, collision, and settling of black holes, but they tell us little about what happens inside during the merger. Some physicists speculate that certain features of a black hole's interior might survive the collision, potentially leaving subtle imprints in the gravitational waves themselves. Others believe that everything inside gets completely scrambled, leaving no trace of prior structure. Future gravitational wave detectors may one day be sensitive enough to detect these patterns, revealing hidden differences in black holes that were once invisible to us. Even beyond these questions, black holes challenge the boundaries of known physics. They are laboratories for extremes, places where general relativity meets quantum mechanics, where time slows and space curves into unimaginable shapes. Each black hole may hold unique insights about the universe, providing glimpses into conditions impossible to recreate on Earth. Supermassive black holes might allow matter to linger longer, opening the possibility for exotic interactions and unexpected phenomena. Primordial black holes may give clues about the very earliest moments after the Big Bang, when the universe was denser, smaller, and stranger than anything familiar. Rotating or charged black holes push the limits of our mathematical understanding, hinting at pathways to other realms of space or new forms of matter. In physics, there is a very unusual and intriguing idea that might sound almost unbelievable at first. It goes like this. If you take all the mass in the observable universe, all the stars, all the galaxies, all the planets, every single atom and particle, and consider how strong their combined gravity is, you can calculate a special value called the Schwarzschild radius. This radius is, in essence, the size a sphere would need to be if you packed all that mass into it for it to become a black hole. Now here comes the strange part. When you actually do the calculation, the resulting radius turns out to be roughly the same size as the universe itself. This leads to a fascinating and unsettling question. Could the universe already exist inside a black hole? If the total mass of everything we know fits within its own Schwarzschild radius, then in a certain sense, it meets the basic requirement for being a black hole. At first, this seems like a numerical coincidence. After all, our universe is not collapsing inward, it is expanding, and we do not feel any crushing gravitational pull. But the mathematics behind black holes is more subtle than just collapse. Black holes are not defined solely by the fact that matter collapses. They are defined by the shape of space-time they create. If the shape of the universe on the larger scales resembles the shape inside a black hole, then this question becomes more than just a coincidence. It becomes serious and worthy of study. Some physicists have explored this idea by comparing the inner structure of black holes to models of our expanding universe. The results are surprising. In some models, the way time passes, the way distances stretch, and the way light moves in an expanding universe looks remarkably similar to the properties of space-time inside a black hole. Deep inside a black hole, beyond what is called the event horizon, space and time themselves swap roles. A direction that normally counts as space effectively becomes a direction in time. In a similar way, in an expanding universe, space itself stretches in every direction, and the earliest moment we can identify, the Big Bang, acts almost like a horizon. It is a limit. Nothing can be observed or come from before it, much like the edge of a black hole traps everything beyond it. There are even more technical reasons to take this idea seriously. In the 1960s, the physicist Andrei Sokurov proposed that the Big Bang might actually be the other side of a black hole. Instead of being a collapse to nothing, it could be a kind of bounce. Later, other researchers expanded on this, suggesting that the singularity inside a black hole, the point where matter is crushed to extreme densities, might actually give rise to a new universe. Matter and energy that falls into a black hole might not vanish into nothingness. It could instead flow into a new space, a new cosmos, like a seed growing into something entirely new. Some solutions to Einstein's equations even allow for black holes to connect to other regions of space-time, possibly forming baby universes on the other side. From the outside, a black hole appears simple and small, but inside it could hide the birth of an entire universe. This perspective completely changes the way we think about black holes. Instead of being endpoints where physics breaks down, they could be beginnings, places where new universes start. If this is possible, then perhaps our universe itself began this way, not from nothing, but from the interior of a black hole in some larger, older universe. There is a certain elegance to this idea. It could help explain why our universe has the specific energy, pressure, and temperature conditions that allow stars, galaxies, planets, and even life to exist. Black holes have precise balances of energy and matter. If our universe were inside a black hole, perhaps these conditions are not random at all. They could naturally arise from the physics of black holes in a grander cosmic system. But what does it really mean to say that the universe is inside a black hole? Physically, there is no surface we can cross or point to and call an event horizon. We do not observe an outside parent universe, nor is there anyone outside watching us fall in. Some physicists caution that this idea should be approached carefully. Just because the equations describing black holes and the universe appear similar does not mean the situations are exactly the same. In a traditional black hole, an outside observer can, at least in theory, locate the event horizon. In our universe, no such external viewpoint exists. We experience the expansion of space, the flow of time, and the shape of the universe from within, but there is no way to step back and see the universe as a whole. Other physicists see this as precisely the point. Perhaps there is no outside. Maybe the universe is similar to a black hole, not because it is literally trapped inside one, but because black holes and universes share the same deep underlying structure. Perhaps the laws that govern black holes also govern entire universes. In this vision, every black hole that forms could be the beginning of a new universe. Our universe might itself be one among countless others, each born from the collapse of stars in a parent universe. And each black hole in our own universe might be a seed for yet another hidden cosmos beyond its event horizon. This leads to a bold idea called cosmological natural selection, which has been explored by scientists such as Lee Smolin. In this concept, black holes are not the destructive endpoints we once imagined. They are engines of creation. Every collapse could generate a new universe, giving rise to a vast, branching network of universes, an eternal cosmic tree, growing and reproducing through the physics of black holes. What once seemed like the ultimate limit in physics, a place where space, time, and matter break down, is now being reimagined as a doorway to new worlds. There is still no direct evidence that our universe is inside a black hole. It remains a theoretical idea, derived from equations rather than observation, but the fact that serious scientists consider it shows just how flexible and strange reality might be. One day, as we learn more about the early universe, about singularities, about quantum gravity, and about the shape of space-time itself, we may discover that black holes and universes are not separate phenomena. They could be different expressions of the same fundamental principles, linked by geometry, energy, and the deep logic of space-time. The ultimate question remains, does the cosmic horizon of our universe act in the same way as the event horizon of a black hole? No matter how advanced our telescopes become, no matter how sharply they can peer into the night sky, there is a hard limit to how far we can see. This limit does not come from clouds of dust, darkness, or any fault of our instruments. It arises from something much more fundamental, the nature of light itself, and the way the universe expands. This invisible boundary is known as the cosmic horizon. Beyond it, space continues, galaxies continue, stars continue. Yet the light from those distant regions has not had enough time, since the beginning of everything, to reach our eyes or our instruments. It is not simply a matter of distance. According to the rules of physics, it is impossible for us to ever see what lies beyond. And when you think about it, this cosmic horizon behaves in ways that are strangely similar to something else in the universe, the event horizon of a black hole. The event horizon of a black hole marks the point of no return. From the outside, it is a one-way boundary. Matter and information can cross inward, but nothing can ever escape. Light itself cannot flee. To an observer outside, the black hole hides its innermost secrets, and no matter how clever or powerful you are, you cannot peer past that boundary. Now, imagine the cosmic horizon. We can look across billions of light years, gazing at galaxies as they were billions of years ago, seeing the echoes of the distant past. But this ability has a limit. Beyond a certain point, galaxies are moving away from us so quickly, pushed along by the expansion of space itself, that their light will never, ever reach us. This is not because galaxies are moving through space faster than light, which is impossible. It is because the very fabric of space between us and them is stretching faster than light can travel. It is like trying to run on a treadmill that keeps stretching beneath your feet. No matter how fast you run, the floor moves faster than you can manage, and eventually you cannot make any progress at all. This creates a horizon, a boundary that is absolute and unavoidable. Are these two horizons, the cosmic horizon and the black hole event horizon, truly the same, or are they just similar in appearance? To answer that, we need to look at how each one works. A black hole's event horizon is local. It surrounds a single object, a point in space with gravity so strong that nothing nearby can escape. Its shape is determined by the mass of the black hole and its spin. From the outside, the horizon appears fixed and constant, a solid line marking the boundary of the black hole's influence. The cosmic horizon is different. It is not tied to a single object. It is a property of the universe itself, and it changes over time. In the earliest moments of the cosmos, the horizon was much smaller, because there had been little time for light to travel. As the universe grew older, the horizon expanded, allowing us to see farther and farther into space. But now, billions of years later, some galaxies are beginning to slip away again. Those we see today may eventually vanish from view. Their light will no longer reach us, not because they have moved or disappeared, but because the horizon has overtaken them. Even though they are different in origin, the two kinds of horizons share surprising features. Both hide information, both set limits on what can be known, and both even have a temperature. That sounds strange. How can a horizon have a temperature? But in the strange world of quantum physics, horizons are not empty voids. They are active, dynamic features of reality. A black hole emits a faint glow called Hawking radiation, produced by quantum effects near its event horizon. Similarly, the cosmic horizon has its own tiny temperature, linked to the rate at which the universe expands. It is unimaginably cold, far colder than the emptiest vacuum we can imagine, but it is not zero. Even in empty space, far from any star, there is a whisper of thermal energy, a faint reminder of the horizon that bounds us. This raises deeper questions. Is the cosmic horizon merely a limit to our knowledge, or is it a real, physical feature of space and time? If it is real, does that mean we are, in a sense, trapped inside something resembling a black hole, except on a universal scale? Some physicists have explored the idea of a horizon for observers like us, not just inside a black hole, but across the entire cosmos. This is sometimes called a de Sitter horizon, named after a solution to Einstein's equations in which space expands forever. In this scenario, every observer has a personal horizon, a limit to what can be seen, shaped by where they are and how space expands around them. These horizons behave in many ways like a black hole's event horizon. They block information, they carry entropy, they even radiate, at least in theory. If this is true, then perhaps the universe is more like a black hole than we ever imagined. Not a black hole filled with crushed matter, but a black hole of knowledge and experience, bounded by a horizon that defines the limits of what we can know, what we can observe, and what we can ever reach. We are not inside a black hole, but we are surrounded by a horizon nonetheless. It is not a surface of matter or a wall of stone, but a surface of limits, a frontier beyond which our signals, our measurements, and even our understanding cannot extend. Horizons are also relative. In a black hole, someone falling inward experiences no sharp boundary. They do not feel the event horizon as a wall. To them, space continues. But an outside observer sees a clear, permanent line marking the black hole's influence. The same is true of the cosmic horizon. Depending on where you are, your horizon may differ slightly from that of someone else. You may see a different portion of the sky, experience a different limit to what can ever be known. Horizons are not absolute. They emerge from the way observers interact with the universe, shaped by motion, perspective, and the relentless flow of time. Reality itself may differ for each observer, not merely in appearance, but in what actually exists for them. This leads to a striking idea called horizon complementarity. No single observer can perceive all of reality. Each observer receives a slice, a personal portion of the universe that defines what is real for them. Inside a black hole, the person falling inward and the person watching from afar each experience different versions of events, and both are valid. In the universe, each of us lives within a cosmic horizon determined by our past, our motion, and our position in space. Beyond that boundary, there are events we cannot witness, galaxies we cannot reach, and truths we cannot uncover, not because of our lack of ingenuity, but because of the fundamental rules that govern space and time. Imagine for a moment that the universe we live in has edges, not solid walls like the ones that surround a room, but invisible limits, boundaries beyond which we simply cannot see. These limits are not just curiosities, they might hint at the deeper, hidden structure of reality itself. Some physicists have begun to wonder if the universe, in its entirety, might work a bit like a hologram, a projection of information from a distant, higher dimensional surface. The idea that information and space might be connected in such a strange way began to take shape in the 1970s when physicist Jacob Bekenstein made a startling suggestion. He proposed that black holes, those enigmatic objects whose gravity is so intense that not even light can escape, might not erase the information they swallow. Instead, the information might be stored on the black hole's surface, the event horizon, the invisible boundary surrounding it. Surprisingly, the amount of information a black hole could contain did not depend on its volume, the three-dimensional space inside, but on the area of this surrounding surface. In other words, everything that fell into a black hole might leave a record, not in the depths, but on the edge. Stephen Hawking, a few years later, added another twist. He showed that black holes are not entirely black. They emit a faint radiation due to quantum effects near the horizon. Over immense periods of time, this radiation causes the black hole to shrink and eventually vanish. This raised a perplexing question. If the black hole slowly disappears, and the information is stored on its surface, what happens to that information? Does it vanish? That would contradict the rules of quantum mechanics, which say that information can never be destroyed. Or is it somehow encoded in the Hawking radiation itself, scrambled in ways we cannot yet decode? Physicists wrestled with this information paradox for decades. Some believed that information might be lost forever, challenging the very foundations of physics. Others argued that the information must somehow be preserved. Eventually, a radically new perspective began to emerge, one that turned our understanding upside down. What if the information about everything inside a black hole isn't actually inside at all? What if it is completely represented on the surface? Not just stored there, but fully encoded, like a cosmic blueprint. This led to the idea of a holographic universe. Most people have seen holograms, a flat surface that, when viewed in the right light, appears three-dimensional. The image seems to have depth, even though it exists on a two-dimensional plane. In the holographic principle, this is not an illusion. Instead, it suggests that our entire three-dimensional reality, including space, time, gravity, and everything we observe, could be described entirely by information residing on a two-dimensional surface. Picture a cube of space. The cube contains stars, planets, atoms, and all the matter and energy within it. Normally, one might assume that the information is spread throughout the volume of the cube. The holographic principle, however, suggests that the true amount of information is proportional to the area of the cube's surface, not the interior. Just as with black holes, the surface alone could encode everything inside. This concept received a major boost in 1997, when theoretical physicist Juan Maldatina discovered a remarkable connection between two very different physical theories. One theory described gravity in a five-dimensional space, a bulk universe, while the other described quantum fields, without gravity, on a four-dimensional boundary of that space. Although these theories looked completely different on paper, they were mathematically equivalent. Everything that occurred in the five-dimensional universe with gravity had a counterpart in the four-dimensional universe without gravity. It was as if two entirely different languages were telling the same story. This discovery became known as the AD-CFT correspondence, short for anti-de Sitter conformal field theory. While the correspondence applies to a very specific kind of universe, not exactly like our own, it demonstrated that a holographic description of reality is at least possible. It showed that a universe with gravity could be fully described by a theory without gravity, living on a lower dimensional surface. Space and time in the higher dimensional world could emerge entirely from quantum information encoded on the boundary. If such a duality could exist in a special artificial universe, physicists began to wonder, could something similar apply to our own universe? Our universe is expanding, and it is not an anti-de Sitter space. Yet the concept opened a new way of thinking about the relationships between gravity, quantum mechanics, and information. More and more researchers started asking, what if the entire universe we experience is a kind of hologram? If this is true, then everything we perceive, the rotation of planets, the flow of time, the formation of galaxies, might be a projection. The real data of the universe could reside on a distant boundary, far beyond the limits of our observable cosmos. Everything around us would behave as if it were fully three-dimensional, while at a deeper level the rules might come from a flat two-dimensional sheet of information. This idea might sound like science fiction, but it has serious motivations. For one, the holographic principle resolves the black hole information paradox. If the information is on the surface, it is never truly lost. It also offers a potential bridge between quantum mechanics and gravity, two frameworks that have resisted reconciliation for a century. Quantum mechanics preserves information, while gravity allows space to stretch, bend, and even tear. But if gravity emerges from quantum information encoded on a lower dimensional surface, space itself may be a consequence, not a starting point. There is additional evidence pointing in the same direction. When physicists calculate the maximum possible entropy, the measure of hidden information or disorder, inside a region of space, they repeatedly find that it scales with the area of the boundary, not the volume. This pattern shows up in black holes, in quantum field theories, and even in simple thought experiments. It is as if nature is signaling that information fundamentally resides on surfaces, not in volumes. Still, many questions remain unanswered. If the universe is a hologram, where is the screen that projects it? Is it the cosmic horizon, the furthest edge we can see? Is it a mathematical boundary at infinity? Or is it something else entirely, a domain beyond ordinary space, invisible to us? And what does this mean for our experience of reality? If the universe is a projection, does it alter the meaning of existence? Are we, along with everything we see, merely shadows of information? Could time itself be part of the projection? No one knows the answers yet. For now, the holographic principle remains a bold, unproven idea, but one intimately tied to the best theories of physics we have. It invites us to imagine a universe not as a simple collection of matter and energy, but as a vast system of information playing out across a cosmic surface we cannot touch or see. The reality we inhabit may be entirely real to our senses, yet at its deepest level it could be a reflection, a story written on a distant boundary, unfolding like a hologram in the cosmic darkness. For decades, the leading idea of how the universe began has been the Big Bang, a single moment in time when space, time, matter, and energy all seem to burst outward from an unimaginably dense point. It is the origin story of the cosmos, a singular moment when everything we know from the tiniest atom to the largest galaxy came into existence. This event, which occurred roughly 13,800,000,000 years ago, is considered the starting line of the universe. But what if the story is not as simple as a beginning from nothing? What if the Big Bang itself was not the ultimate start, but the result of something even stranger, something hidden and mysterious, a phenomenon we are only beginning to imagine? A white hole? The idea of a white hole is as odd and mind-bending as it sounds. In the realm of theoretical physics, a white hole is essentially the opposite of a black hole. While a black hole is a region in space where gravity is so strong that nothing, not even light, can escape, a white hole is thought to work in reverse. In theory, nothing can enter a white hole, but everything inside it is expelled outward. It is a cosmic fountain rather than a trap. You can think of a white hole as a black hole running backward in time. Instead of pulling everything inward into a crushing point, a white hole pushes everything outward in a violent, unstoppable explosion. Mathematically, if one takes the equations that describe black holes and reverses the direction of time, the result is something that behaves like a white hole. So far, white holes exist only on paper. We have never seen one in the night sky, nor have we detected any direct evidence of their existence. Black holes, in contrast, are abundant. We know they exist because we observe the stars that orbit around invisible centers of gravity, the X-rays emitted when matter falls into them, and the gravitational waves that ripple through space when two black holes collide. White holes, however, remain purely hypothetical. Yet the equations describing them are internally consistent, at least theoretically. They make sense on paper, even if nature has not shown us a real example. At first glance, one might wonder why we would even bother connecting white holes to the Big Bang. After all, the Big Bang already looks like an explosion, a sudden, massive expansion of hot, dense matter into the emptiness of space. But the connection between white holes and the Big Bang is more than superficial. A white hole is not simply a random eruption. It is often envisioned as the outward burst of something that was previously trapped. It is the rebound of material compressed in an extreme environment. If the Big Bang were, in fact, the explosion of a white hole, then the matter and energy that make up our universe today might have originally been trapped inside a black hole in some other, larger universe. In this view, our universe could be the interior of a white hole, formed when a black hole in a different cosmic system collapsed and rebounded, creating an entirely new region of space and time. Some modern theories of physics, particularly those in the field of loop quantum gravity, suggest that black holes do not end in true singularities, where matter is crushed to a single point of infinite density. Instead, the matter falling into a black hole might be compressed to an extreme but finite density, and then, rather than being destroyed, it rebounds. If this rebound occurs, the other side of the black hole could resemble a white hole, a place where all the trapped matter bursts outward into a new region of space. In this sense, every black hole could potentially serve as the seed of a new universe, a hidden cosmic nursery. From the perspective of beings living inside such a universe, there would be no hint of its origin. They would observe their cosmos expanding outward, tracing its history back to a hot, dense beginning, just as we do with our own universe, never suspecting that their Big Bang was born from a black hole somewhere else entirely. This concept offers a fascinating resolution to one of the deepest mysteries about time. If we say that time began with the Big Bang, then we're left asking, where did time itself come from? What set the universe in motion? If our universe emerged from the interior of a black hole in another universe, then time did not begin with our Big Bang. It already existed. The moment we call the Big Bang would be just one phase in a much larger cosmic timeline, a continuation of events that started elsewhere. Time, in this scenario, is not created from nothing but inherited, flowing from a parent universe into a child universe through the extraordinary mechanism of black hole collapse and white hole rebound. The white hole idea also offers a potential solution to the puzzle of black hole interiors. If nothing ever escapes a black hole, then where does all the matter go? Is it lost forever? Does it vanish from existence? Or might it find a way to reappear somewhere else? The white hole concept provides an elegant escape hatch. Matter and energy swallowed by a black hole are not annihilated but recycled. They could re-emerge in a new universe, in a different form, providing a continuous cosmic cycle of destruction and creation. Of course, the white hole hypothesis is not without its challenges. For one, we have never observed a white hole directly. Their very nature might make them invisible or unobservable with current technology. Additionally, the specific conditions needed to produce a white hole could be exceedingly rare or impossible in our universe. Finally, we are uncertain whether the known laws of physics would allow a black hole to give birth to an entirely new universe. Despite these hurdles, intriguing hints encourage physicists to keep exploring the idea. One hint comes from the uniformity of the cosmos. When we examine the universe today, we see it is remarkably smooth and even. The cosmic microwave background, the faint afterglow of the Big Bang, is nearly the same temperature in every direction, even across regions of space that could never have exchanged information. This uniformity is surprising. How did distant regions agree on the same temperature when light could never have travelled between them? This is called the horizon problem, the theory of cosmic inflation, which posits that the early universe expanded faster than the speed of light, helps explain this phenomenon. But so does the white hole idea. If the matter that now fills our universe originated from a black hole in another universe, it could have been tightly compressed before rebounding. In this compact state, energy and temperature could equilibrate, producing a uniform cosmos once it expanded into a new space-time region. In other words, the white hole model provides a different, yet complementary explanation for the observed smoothness of the universe. The white hole concept also interacts with other profound principles in physics. One is cosmic censorship, a rule in general relativity suggesting that singularities, points of infinite density, must always be hidden behind an event horizon so that no observer can directly witness them. If true, this means we should never see the true core of a black hole. But the Big Bang seems to present us with a visible singularity, a moment of extreme density and energy that we can, in principle, observe through the cosmic microwave background and other relics. If the Big Bang were actually a white hole, it could be the visible side of a singularity in another universe, sidestepping cosmic censorship while maintaining theoretical consistency. Some versions of this idea even tie into the holographic principle, a theory suggesting that space and time are not fundamental but emergent, arising from information encoded on a boundary or surface. In this view, the formation of a new universe from a black hole could be seen as a transformation in how quantum information is structured. A black hole in one universe, when viewed through this lens, could appear as a white hole in another, not because matter magically passes through, but because the underlying information rearranges itself, giving rise to a new space-time region. Researchers have also explored the possibility of white holes forming naturally within our own universe, rather than only as a consequence of a black hole in another universe. Some models suggest that as a black hole ages and loses mass through processes such as Hawking radiation, it might eventually transition into a white hole state, releasing all the matter it had absorbed. This could occur after billions or even trillions of years, a cosmic event far beyond human lifetimes. However, in this scenario, the black hole would not spawn a new universe, but would simply return matter to the existing universe. Still, it demonstrates that the laws of physics allow for the theoretical possibility of a black hole rebounding as a white hole, hinting that such transformations are at least mathematically plausible. All of this leads to a tantalizing question. What if our Big Bang was the result of a white hole, not in our own universe, but in some other, larger cosmos? Perhaps it was a one-time, unique event. Our universe, with its 13,800,000,000 years of history, might be the interior of a white hole that formed when a black hole collapsed somewhere else entirely. Every galaxy, every star, every particle of matter in existence could have been ejected from a cosmic womb hidden beyond our observational reach. If true, it would mean that the Big Bang was not the absolute beginning, but a remarkable event in a vast interconnected network of universes, each potentially born from the collapse of black holes in yet another universe. This vision of the cosmos is both humbling and awe-inspiring. It suggests that the universe is not a solitary creation, but part of a potentially infinite chain of cosmic evolution. Black holes are not merely destructive objects, but maybe the seeds of new worlds, recycling matter and energy across the vast expanse of existence. White holes, still unobserved and purely theoretical, could represent the other side of this cosmic cycle, where the collapsed cores of one universe give rise to the fiery birth of another. From this perspective, the Big Bang is not just a beginning, it is a doorway, a cosmic rebound echoing through the grand, unending dance of space, time, and energy. In contemplating this possibility, we are forced to expand our imagination beyond the visible universe, beyond the stars and galaxies we can see, into a realm where universes beget universes, where black holes become cosmic cradles, and where the Big Bang is just one dramatic, brilliant chapter in a story that may stretch on forever. It reminds us that the universe we inhabit might be both ancient and new, connected to a larger multiverse, and that the question of our origin may be far more intricate and beautiful than the simple idea of a singular beginning. It is a story of continuity, of transformation, and of the endless recycling of matter and energy across the vast expanse of reality, suggesting that even in the seemingly empty darkness of a black hole, a new cosmos may be waiting to burst forth, lighting up the void with creation once again. Imagine a universe that isn't just expanding endlessly, but one that, at some distant time, could slow down, stop, and begin to fold in on itself. Right now, we live in a cosmos that stretches outward, galaxies drifting apart as space itself grows. But this hasn't always been the case, and it might not last forever. In certain models of how the universe works, the relentless expansion could someday give way. Gravity, pulling on all matter and energy, might eventually win. Slowly, inexorably, it could halt the growth of space and then reverse it. Galaxies would edge closer together, stars would exhaust their fuel and dim, matter would clump and compress, space itself would shrink, and time, strange as it sounds, might seem to speed up as everything rushed toward an ultimate collapse, a dramatic finale sometimes called the Big Crunch. This Big Crunch is the mirror image of the Big Bang. While the Big Bang was a sudden explosive birth, the Big Crunch is a slow, unavoidable implosion. The universe would compress into an unimaginably tiny point, matter and energy packed together so densely that the rules of physics we know would no longer make sense. It would be a singularity, the same kind of singularity thought to lie at the heart of a black hole. And just as the death of a massive star can give rise to a black hole, perhaps the death of an entire universe could spark the birth of something entirely new. Some scientists imagine this cosmic collapse not just happening within our familiar three dimensions of space, up, down, left, right, forward, back, plus time, but inside a larger, higher dimensional space. These extra dimensions are ones we cannot perceive directly, yet they might exist, hidden beneath the fabric of reality. In such a space, our entire universe could contract, shrinking in a way that, from the outside, would look very much like a black hole forming. From our internal perspective, though, this collapse could appear as the birth of a brand new universe, expanding outward, oblivious to the origin from which it sprang. These ideas are not just flights of fancy, they appear in several theories of modern physics. One such idea is called cosmological natural selection. It proposes that every black hole could create a baby universe on the other side of its event horizon. These new universes might have slightly different physical laws, gravity might be stronger or weaker, particle masses might differ, the balance of forces might shift. Over vast stretches of cosmic time, universes that are adept at producing black holes would leave behind more offspring, while those less suited to forming them would fade away. In this way, the cosmos could evolve, much like life on Earth, through a strange universal natural selection. Our universe, with its delicate mix of stars, galaxies and black holes, might exist because it is especially fertile, able to give rise to new universes. Other frameworks, such as loop quantum cosmology, suggest that the end of one universe naturally leads to the beginning of another. Some even go further, imagining that every black hole in our universe could be a seed for a completely separate universe, branching off into its own space and time. From inside this newborn universe, it would feel like a fresh beginning. From a broader vantage point, it would resemble just one leaf on an immense, ever-growing cosmic tree. Taken together, these ideas paint a vision of a multiverse, a vast, perhaps infinite collection of universes, each born from the death of another, each evolving, expanding and generating offspring in an endless cosmic cycle. But where does all of this occur? If a collapsing universe becomes like a black hole in higher dimensions, what is that space around it? What does it mean for one universe to exist inside another? We do not yet have concrete answers. These concepts challenge our deepest understanding, asking us to think beyond what we can observe, beyond what our current mathematics can fully describe. If black holes continually give birth to new universes, and if those universes eventually produce stars that die and create more black holes, the cycle could continue forever. Entire universes could spawn other universes in a cosmic chain reaction. Not just stars and galaxies, but entire realities reproducing themselves, one generation giving rise to the next. Some physicists call this the fecund universe idea, a universe that is fertile, always creating new universes. In this grand vision, our own cosmos is merely one among countless others, part of a larger pattern that stretches far beyond the edge of what we can see, beyond the limits of our time, beyond the horizon of our imagination. These other universes may be forever beyond our reach, yet if they exist, we are part of something far grander than we have ever dared to imagine. This framework could also explain why our universe seems so finely tuned. The exact strength of gravity, the precise masses of fundamental particles, the delicate balance of the forces, all of these may not be coincidences. They could reflect the requirements for forming stars and black holes, ensuring that our universe is fertile enough to produce offspring. In other words, our cosmos may not be a stroke of luck, but the outcome of a long, ongoing cosmic history, shaped by the need to give birth to future universes. And yet, the question remains, how could we ever know if we live inside a black hole? From our vantage point, the universe feels enormous and open. We observe galaxies drifting apart, we map the faint afterglow of the cosmic microwave background, and we detect light from billions of light years away. But none of this tells us what lies beyond the visible universe, nor does it reveal the ultimate nature of space-time itself. If our entire universe were merely the interior of a black hole, what traces of that truth would remain? What subtle signs might hint at this hidden cosmic reality? The very first thing to grasp is that, If we truly are living inside a black hole, we would never see its edges. From the inside, the boundary, the so-called event horizon, would be far beyond anything we could ever detect or observe. Space itself would curve in such a strange and extreme way that light, along with everything else, would be drawn inward endlessly, trapped in a loop that never lets anything escape. From our point of view, the universe would appear infinite, stretching on forever in every direction, even though, in reality, it would have a limit, a boundary we could never reach. This might sound like a strange idea, but in many ways, it already resembles how our universe behaves. We do not see an edge. When we look out into space, all we see are galaxies growing fainter as they recede into the distance. Their light stretches, becoming redder and redder, until eventually it fades into nothingness, invisible to our instruments. Could this cosmic redshift, the stretching of light from distant galaxies, actually be a hint of the deep curvature of space caused by a surrounding black hole? Some researchers believe this might indeed be the case. Mathematics provides the most compelling clues. The equations that describe the expansion of space in our universe, the way it grows larger over time, bear a striking resemblance to the equations that describe the space inside a rotating black hole. In both scenarios, space does not remain static, and time does not flow at the same rate everywhere. Clocks tick differently depending on location, and distances warp in strange ways. The similarities are so precise that some scientists wonder if they are more than a coincidence. Perhaps, they argue, the shape and behavior of our entire cosmos are determined by the conditions present at the birth of a black hole somewhere beyond the space we see. The large-scale shape of the universe might offer yet another clue. If we could measure the overall geometry of space, not just in our local neighborhood, but across the cosmos as a whole, we might discover something remarkable. For instance, if the universe is closed, meaning that it curves back on itself, like the surface of a giant sphere, it would indicate that the universe is finite. A finite universe wrapped up in higher dimensional space could match the shape expected for the interior of a black hole. In this view, our universe would be a bounded volume with its own internal geometry, completely disconnected from whatever lies outside. Space would be trapped, folded in on itself, and yet from within it would appear endless. There are also deep questions about information and entropy, ideas that hint at the very foundation of reality. Inside a black hole, the amount of information that can be stored does not scale with the volume of the black hole, as one might expect, but rather with the area of its event horizon. Some physicists have wondered whether our universe might follow a similar rule, suggesting that reality itself could be holographic. If this idea proves correct, it would provide a powerful indication that we are indeed living in a space shaped by black hole physics, where the information of everything inside is encoded on a boundary we cannot reach or see. Clues might also come from the cosmic microwave background, the ancient afterglow of the Big Bang. This light, travelling across billions of years, has been stretched into microwaves, forming the faint uniform glow that fills the universe. But within that glow, tiny patterns, subtle irregularities and faint asymmetries exist. If our universe formed from matter collapsing into a black hole, the extreme turbulence, rotation, and immense energies involved in that process could leave lasting imprints on this ancient radiation. Unexpected alignments or irregularities in the cosmic microwave background could be faint whispers from a time when our cosmos was shaped by the collapse of matter into a singularity. Another fascinating consideration is the role of spin. Most black holes rotate because the stars that created them already had angular momentum. If a spinning black hole forms a new universe, that spin could influence how that universe expands or how galaxies within it move. If astronomers were to detect even a subtle, large-scale rotation in the universe, it might point to an origin story tied to a parent black hole. Angular momentum inherited from that black hole could shape the motions of stars and galaxies on the grandest scales. Thinking along these lines raises yet another possibility. What if the universe contains something missing? Our cosmos obeys rules, yet it is also filled with puzzles. Dark energy, the mysterious force accelerating the universe's expansion, is one of the greatest enigmas. Its nature is unknown, and yet its effects are undeniable. If we are inside a black hole, perhaps dark energy is not a substance at all, but a natural consequence of being trapped in a region of extremely curved space. In this picture, the accelerated expansion we observe is not caused by some exotic substance. It is simply how space behaves when confined in a gravitational well as extreme as a black hole. Even the tiniest building blocks of spacetime might offer hints. If space and time are not continuous, but instead made of discrete pixel-like units, this digital structure would align with the idea that the universe has an information budget, a strict limit to the amount of information it can contain. Black holes naturally impose such limits. If the rules of quantum gravity confirm that all of space follows the same limit, it could support the hypothesis that our visible universe exists inside a larger structure with boundaries, just like a black hole. High-energy cosmic rays, the fastest and most energetic particles in the universe, may carry yet more clues. If particles with energies beyond a certain cutoff are observed, or notably absent where they should appear, this could point to extra dimensions or hidden boundary conditions shaping our universe. Some of these effects may only make sense if the visible cosmos is, in fact, curled up inside a higher dimensional object, a black hole of immense scale. There is no simple experiment to prove any of this. We cannot send a probe to the edge of the universe and step outside to look back. We cannot escape to see the larger space that might contain us. But science offers another path. We can look for patterns, for places where the universe behaves differently than an unbounded free space should. If these patterns match the predicted behaviors of black hole interiors, it could revolutionize our understanding of reality. Entirely new concepts about space, time, and the very origins of existence would have to be reconsidered. Every clue, from the stretching of light and the subtle rotations of galaxies to the smallest irregularities in the cosmic microwave background, might tell a story far stranger than we have imagined. A story in which our universe is not the entire story of reality, but rather a single chapter within a far greater, deeper, and perhaps incomprehensible cosmic structure. A universe born from the collapse of matter into a black hole, shaped by forces and geometries far beyond ordinary experience. In such a vision, the cosmos we inhabit is both familiar and alien. It stretches endlessly before our eyes, yet it is contained within an invisible shell. Galaxies drift apart as space itself flows outward, while information and energy obey strict hidden rules. Dark energy and cosmic redshift are not mysteries, but signatures of our confinement, echoes of a deeper, unseen reality. Even time itself may bend and flow differently at scales we cannot perceive, guided by the invisible curvature of the space that encloses us. The thought is at once humbling and exhilarating. Everything we know, all that we see in the night sky, every particle in our bodies might exist inside the interior of a gargantuan black hole, a structure so vast and complex that it defines the very nature of our reality. And yet, from our vantage point inside, the universe appears infinite, boundless, and eternal, a perfect illusion crafted by the extreme geometry of space and time. Ultimately, the idea challenges every assumption we have about beginnings and endings, inside and outside, finite and infinite. It suggests that the cosmos is far stranger than we imagine, that our universe may be a shadow of a deeper, hidden structure, and that the rules of black hole physics might not just govern the fate of collapsed stars, but the fate of all that exists. If this is true, we're living inside the most extraordinary laboratory imaginable, a place where every galaxy, every photon, and every quantum fluctuation carries the imprint of a reality we're only beginning to glimpse. In the last few decades, scientists have been struggling with one of the most mysterious questions in modern physics. What really happens to information when a black hole slowly fades away? The puzzle is not about the great devouring presence of black holes alone, but about the delicate details of how they disappear, drop by drop, through a process called evaporation. To understand this, physicists have turned to new tools borrowed from quantum computing and the strange world of quantum entanglement, where particles behave as if they are secretly linked no matter how far apart they may be. One of the most important ideas to come out of this effort is something called the Page curve, named after the physicist Don Page. This curve is not just a line on a piece of paper, it is a story told in the language of time and information. Imagine drawing a graph that shows how much information seems to be locked away inside a black hole as it slowly radiates energy. At first, the line seems to say that all the information is being swallowed up, disappearing into darkness as if erased forever. The early stages of evaporation look like a one-way trip into nothingness, as though the universe has a shredder built into its fabric. But then, something remarkable happens. After a certain stretch of time, the graph turns upward. The radiation, which at first seemed to be meaningless and random, begins to carry patterns. More and more information leaks out. By the time the black hole has finally evaporated completely, the curve shows that the lost knowledge is not lost at all. It has simply been delayed, scrambled and hidden, but not destroyed. The universe in this picture keeps its promise of memory. Nothing is truly erased, only transformed. This discovery suggests something both thrilling and baffling. Black holes may behave like the most complex quantum computers imaginable. They take information, twist it in ways so complicated that no human mind could hope to unscramble it easily, and then release it again after long ages. They do not destroy data, but they guard it fiercely and release it only in strange, subtle patterns. Scientists are still trying to uncover the exact tricks that black holes use in this cosmic game, but they have begun to make progress by studying simplified versions of black holes. These toy models are not meant to capture the full horror and beauty of the real thing, but they allow the mathematics to be handled without collapsing under its own weight. Some of these models have even managed to reproduce the page curve, giving confidence that this picture is not just wishful thinking. Other studies show that information might leak out bit by bit through the complicated patterns of entanglement that tie together the black hole and the radiation it emits. The quantum links between the inside and the outside could allow pieces of knowledge to sneak through the veil. Yet, as with any daring idea, not everyone agrees. Some physicists insist that this is too gentle a solution, that something more radical must be happening at the edge of a black hole. That radical idea is called the Firewall. According to this proposal, the smooth, calm edge of a black hole, the place we call the event horizon, is not smooth at all. Instead, it might be a searing wall of energy so intense that anything touching it is burned to ash instantly. This firewall would shred information before it even has a chance to cross inside, solving the paradox by rewriting the very structure of black holes themselves. To understand why this is so shocking, one has to recall a central principle of Einstein's general relativity, known as the equivalence principle. This principle tells us that, in free fall, you cannot feel gravity. If you were drifting in space and fell into a gigantic black hole, you would not sense anything unusual as you passed the horizon. The crossing would be as calm as floating in a quiet ocean. Only far later, near the center where the Singularity waits, would you encounter the true danger, where space itself ends and all known physics breaks down. The journey to that doom, at least until the very end, would be surprisingly peaceful. The firewall idea destroys this calm picture. Instead of gliding gently into the darkness, you would meet instant death at the edge. The very moment your body touched the horizon, it would be torn apart and incinerated by an invisible sheet of raw energy. This is a direct assault on the equivalence principle. If true, it means Einstein's graceful vision of space and time is broken in one of the most extreme environments in the cosmos. The reasoning behind the firewall proposal comes from the laws of quantum mechanics. One of these laws is the so-called monogamy of entanglement. In simple words, it means that a single piece of quantum information cannot be perfectly entangled with two different partners at once. If Hawking radiation, the glow emitted by black holes, is to carry information away, then the new radiation leaving the black hole must be entangled with the earlier radiation already emitted. But that means it cannot also be entangled with what remains inside the black hole. Something has to give. Physicists faced a painful choice. If they wanted to preserve the rules of quantum mechanics, if they wanted to save information, they had to sacrifice the smooth horizon promised by relativity. Out of this sacrifice, the firewall idea was born. In the year 2012, a group of scientists, Ahmed Almeri, Donald Marolf, Joseph Polchinski and James Sully, published a bold paper proposing that the event horizon might be replaced with a wall of blazing energy. They emphasized that this wall would not be visible to distant observers, but for anyone unlucky enough to fall in, it would mean instantaneous destruction. Their work ignited one of the most intense debates in theoretical physics. The reason the debate became so fierce is clear. If firewalls are real, then the equivalence principle, one of the cornerstones of Einstein's relativity, is false at the boundary of black holes. Space-time would not be smooth, the ride across the horizon would not be gentle. Instead, relativity itself would shatter under the weight of quantum truth. Gravity, as the graceful bending of space-time, would lose its power at the very edge of black holes. That is a staggering price to pay just to keep information safe. It suggests that our entire understanding of what black holes are must be rebuilt from the ground up. Yet, many physicists remain unconvinced. They see the firewall as an act of desperation, an extreme step taken when the puzzle is still only half solved. They believe that another way exists, one that does not force us to destroy the harmony between relativity and quantum mechanics. Some argue that quantum laws themselves may be more flexible than we realize, that information might escape in ways we have not yet discovered. Others suggest that our understanding of entanglement may need to be reshaped when gravity is involved. There is also a more daring proposal, that space-time itself is not fundamental at all, but is woven out of patterns of entanglement. If this is true, then the entire firewall paradox may be built on a false assumption. Black holes and their radiation may be more deeply connected than we imagine. Perhaps the inside of a black hole is not cut off from the outside universe, but is secretly tied to it through hidden bridges. This brings us to another extraordinary idea known as EPR. The letters ER refer to Einstein and Rosen, who described wormholes, and EPR refers to Einstein, Podolsky, and Rosen, who described entanglement. The slogan ER learnt EPR means that entangled particles might actually be connected through microscopic wormholes. In this picture, the interior of the black hole could still talk to the outside world through these secret tunnels in space-time. Information could escape not through fire and destruction, but through these hidden threads linking radiation to the black hole itself. If this vision is correct, then the smooth horizon of relativity can be preserved, and firewalls are unnecessary. The paradox dissolves, not with violence, but with a deeper unity between gravity and quantum physics. Information survives, horizons stay smooth, and the universe remains whole, though in a way far stranger than Einstein himself ever imagined. The choice between firewalls and wormholes is not just a technical argument, it is a window into the heart of reality. If firewalls are real, then our most trusted principles about space and time collapse at the edge of black holes. If they are not real, then we still face a mystery. How can information escape without breaking the rules of quantum mechanics? This is why black holes are more than astronomical curiosities. They are testing grounds for the deepest ideas in physics. They force us to ask whether reality is continuous or fractured, whether gravity bends smoothly or breaks sharply, whether the universe remembers or forgets. Every debate about horizons, entanglement, and firewalls is really a debate about the meaning of the cosmos itself. The answer will not only tell us what black holes truly are, but also whether the laws we hold most sacred, relativity, quantum mechanics, the unity of space-time, are the final truth or only stepping stones to something greater. Black holes, with their silent hunger and their evaporating whispers of radiation, stand as the most severe examiners of human thought. They challenge our best ideas and laugh at our incomplete theories. Whether the horizon is soft or burning, whether information escapes by radiation, wormholes, or hidden laws we have yet to dream of, one thing is certain. Black holes are not simply prisons of darkness. They are laboratories of the ultimate mysteries, pressing us closer and closer to the edge of knowledge. In the great theatre of the universe, where stars live and die and galaxies swirl like dancers in an endless ballet, black holes stand as some of the most mysterious characters. These objects are so dense that even light itself cannot escape their pull once it gets too close. Around the edges of a black hole lies the event horizon, a boundary that marks the point of no return. Once anything crosses it, whether light, matter, or energy, it is trapped forever. But as unyielding as black holes seem, they are not the silent, eternal prisons we once thought. They have a faint, ghostly whisper, a strange radiation that leaks from their edges. This phenomenon is known as Hawking radiation, named after the great physicist Stephen Hawking, who first described it in the 1970s. The idea behind Hawking radiation is at once simple in words, yet deeply puzzling in meaning. It all begins with the fact that what we call empty space is not truly empty. Thanks to the odd rules of quantum mechanics, space constantly flickers with tiny bursts of activity. Invisible to the eye, pairs of particles appear out of nothing, live for the briefest moment, and then vanish again. These are called virtual particles, and they are constantly being created and destroyed everywhere in the cosmos. Normally, these pairs destroy each other so quickly that they leave behind no lasting trace. But near the edge of a black hole, something unusual happens. Imagine two partners appearing right on the rim of the event horizon. In a split second, one partner is pulled inward, falling helplessly into the black hole, while the other manages to escape outward. The particle that escapes becomes real, breaking free into the wider universe. For that to happen, the black hole itself must give up a tiny portion of its energy to allow the particle to exist. Each time this happens, the black hole shrinks ever so slightly. This is the whisper of the black hole, the slow leakage of its energy in the form of Hawking radiation. The process is incredibly slow. If you take a black hole the size of a star, it would take longer than the current age of the universe for it to fully evaporate. Since the universe is already more than 13 billion years old, you can imagine just how glacially slow this fading process is. To us, black holes appear almost eternal, but given enough cosmic time, even they will disappear, leaving behind nothing but a final burst of energy. When Stephen Hawking first proposed this radiation, he believed it was random, like heat pouring from a fire. If that were true, then the information about everything that had fallen into the black hole would be lost forever. Imagine tossing a library full of books into a furnace. The fire radiates heat and light, but the stories within the books are gone. For black holes, this meant that the details of stars, planets, or even people that fell inside would be erased from the universe. But this conclusion created one of the greatest puzzles in physics, the so-called information paradox. If the laws of physics are correct, information should never truly vanish. It may change form, scatter, or become hidden, but it cannot be destroyed. This clashed with Hawking's original picture, where black holes acted like cosmic shredders, wiping out every trace of the past. To resolve this puzzle, many physicists began to suggest that Hawking radiation might not be random after all. Perhaps it carries hidden messages, subtle traces of the information locked inside the black hole, encoded in ways we do not yet understand. If so, black holes are not erasers but mirrors, distorting mirrors that hide the story of what has fallen in, but mirrors nonetheless. The challenge is that this radiation is incredibly faint, weaker than the glow of the most distant stars and almost impossible to detect. On top of that, black holes themselves are restless. Their event horizons are not perfect spheres. They wobble and shift. They vibrate like stretched drums, stirred by the very forces that keep them alive. The more scientists study them, the more they realize that black holes are not silent giants, but cosmic instruments, producing signals in both light and in the fabric of space itself. That brings us to another fascinating clue. Not just the faint light from Hawking radiation, but also the sound black holes might make. Not sound in the usual sense, since space has no air to carry it, but sound as ripples in space-time. When two black holes collide, they merge into one larger hole. In the process, they unleash gravitational waves, ripples that spread outward through the universe like vibrations on a pond. These waves carry the signature of the black holes that made them, their size, their spin, their shape, and their history. After the violent crash, the new black hole does not instantly become still. Instead, it rings like a bell struck by a hammer. These ringing patterns are called quasi-normal modes. They slowly fade, but while they last, they carry deep information about the final black hole. By studying these vibrations, scientists can read the story written into the waves. Already, observatories such as LIGO in the United States and Virgo in Europe have detected these gravitational whispers. From just a few seconds of data, scientists have been able to measure the mass and spin of black holes, billions of light years away, with astonishing accuracy. Some physicists believe that as our instruments improve, we will be able to pick out even finer details in these signals. Within those details might lie clues not only to the outside of black holes, but also to their hidden interiors. This idea is breathtaking, that by listening carefully to the ringing of space-time, we might learn about what is locked beyond the event horizon, a place we thought we could never glimpse. But this raises a haunting question. If no signal can ever escape from inside the event horizon, how could anything we observe on the outside possibly tell us what is happening inside? The possible answer lies in a remarkable idea, that the inside is written on the outside. In other words, everything that falls into a black hole might leave behind a sort of imprint on its surface. The event horizon could act like a cosmic canvas, recording information not in volume but in surface area. This idea came out of studies in string theory and black hole physics. When physicists tried to count the possible states a black hole could have, the many ways it could hold matter and energy, they found something surprising. The number of states did not grow with the volume inside the black hole, as one might expect, but with the area of its surface. This hinted that the surface of the black hole stores all the information about what has gone in. If that is true, then Hawking radiation, gravitational waves, and even the way a black hole pulls on nearby stars are all shaped by that hidden information. In principle, if we learn how to decode these signals, we could uncover the history of everything a black hole has swallowed. For a long time, physicists had a saying, "Black holes have no hair." By this they meant that a black hole could be described with only 3 simple numbers: its mass, its spin, and its electric charge. All other details about what had fallen in were thought to be erased. A star, a planet, or a spaceship would leave behind the same black hole if their mass, spin, and charge were equal. But recent ideas challenge this view. Perhaps black holes do have hair, subtle features that reveal traces of their past meals. These hairs would not be obvious, but they might show up as tiny differences in radiation or delicate patterns in vibrations. If such hair exists, then black holes are not ball destroyers but keepers of memories, holding far more history than we ever believed. The dream is that one day we will learn how to read these whispers, the radiation, the waves, the wobbles, the faint hints of hair. If we succeed, black holes will no longer be cosmic erasers but cosmic storytellers. They will become mirrors reflecting the deep truth of the universe, showing us not only what has fallen into them, but also what the rules of reality themselves are. Perhaps within their whispers lies the key to the greatest mysteries. What happens to information? What is the true nature of space and time? And whether the universe itself is a kind of hologram projected from hidden layers of reality. The year 2015 will forever be remembered as a milestone in science, for it was then that humanity first detected gravitational waves. This discovery was not just another step in the long journey of astronomy. It was a giant leap, one of the greatest breakthroughs in modern science. To understand why, we need to go back to what came before. For centuries, everything we knew about the universe was gathered through light. From the earliest astronomers who gazed at the heavens with nothing more than their eyes, to the giant telescopes that peer across galaxies today, light has always been our messenger. Sometimes it was visible light, the kind that allows us to see stars twinkle. Other times it was radio waves that revealed hidden structures in space, or X-rays that showed us violent explosions and glowing cosmic remnants. But there was a problem. Light, no matter its form, can only show us so much. Black holes, for example, do not give off light at all. They are the ultimate masters of invisibility, swallowing everything that comes too close, even light itself. That is why black holes are often described as invisible giants lurking in the darkness. Their silence made them some of the hardest objects to study, even though their presence could be felt in how they pulled on nearby stars and gas. This is where gravitational waves come in. Unlike light, gravitational waves do not bounce off walls, scatter through dust, or fade away as they pass through obstacles. They move through the universe untouched, carrying with them pure information about the events that created them. Imagine being deaf your whole life, and suddenly being able to hear for the first time. That is what gravitational waves represent to science. A brand new sense, a new kind of tool that lets us probe the deepest and darkest corners of reality itself. Whenever 2 black holes collide, they release a storm of gravitational waves. The event unfolds in 3 dramatic stages. First comes the inspiral, a long and elegant dance where the 2 black holes circle each other, drawing closer with every turn. It is a slow, tightening spiral, like 2 dancers locked in a waltz that grows faster and faster. Then comes the merger, the violent moment of impact when the 2 titans slam into each other with unimaginable force, fusing into one. Yet the story does not end there. After the chaos, the new larger black hole takes time to settle into its final shape. This last stage is known as the ringdown. The ringdown is perhaps the most mysterious phase of all. To imagine it, think of striking a bell. After the strike, the bell does not immediately fall silent. Instead, it vibrates, releasing a clear, fading tone. The new black hole behaves in the same way. It quivers and hums, sending out its own vibration into the fabric of space itself. And hidden within that cosmic note may lie the secrets that scientists have been chasing for decades. This vibration is not random noise. It is made up of what physicists call quasi-normal modes. These are the natural frequencies at which the black hole resonates, just as a guitar string has its natural notes. By studying these frequencies, scientists can learn about the black hole's mass, how fast it is spinning, and how large it is. But there is an even more exciting possibility. Some researchers wonder if these vibrations also reveal something about the interior of black holes, or at least about how the inside behaves during the collision. If all black holes were identical inside, simple pits leading to singularities where all matter is crushed, then the ringdown tones would always sound the same for black holes of the same mass and spin. But if black holes hide more complex internal structures, or if they somehow store information in strange exotic ways, then their vibrations might carry fingerprints of those differences. In other words, each black hole could sing a slightly different song depending on what lies beneath its surface. If we learn how to read those subtle signatures with enough precision, we may one day classify black holes not only by size or spin, but by their hidden inner nature. Since 2015, gravitational wave observatories have already picked up dozens of black hole mergers. These detections have confirmed that black holes exist in abundance, and that they behave largely as Albert Einstein predicted when he published his theory of general relativity more than 100 years ago. But despite these triumphs, we are still at the beginning. The signals we have captured so far are brief and often noisy. The ringdown phase, the most important part for peering into the unknown, lasts for only a fraction of a second, and by the time these waves reach Earth, they are incredibly faint, having travelled across millions or even billions of light years. Yet technology is improving. The current detectors such as LIGO and Virgo are only the beginning. Future observatories promise to be far more powerful. In Europe, the planned Einstein telescope aims to push sensitivity to new heights. Even more ambitious is the LISA mission, a project of the European Space Agency. Unlike ground-based detectors, LISA will float in space, orbiting the Sun in a triangular formation of satellites separated by millions of kilometers. It will listen not for the high-pitched chirps of small black hole mergers, but for the slower, deeper waves created by supermassive black holes at the centers of galaxies. These signals last much longer, sometimes hours or even days, giving scientists far more time to study the fine details of the ringdown. And it is in these details that new physics might reveal itself. Perhaps quantum effects, usually hidden on scales too small to detect, will show up in the way black holes vibrate. Perhaps different theories of gravity will predict slightly different tones, allowing us to test them against one another. If this is true, then gravitational waves will become not just a new way of observing the universe, but a way of testing the very foundations of physics itself. Some of the most daring ideas suggest that black holes may not even have true event horizons, the perfect one-way doors described by Einstein. Instead, there might be something strange just outside the horizon, perhaps a fuzzball of tangled strings as proposed in string theory, or some exotic form of matter unknown to us. If this is the case, then the ringdown signal would not fade smoothly into silence. Instead, it would echo. Imagine shouting into a canyon and hearing your own voice bounce back in faint repetitions. Black hole echoes would be similar, faint aftershocks of the original vibration, delayed and weakened but still present. Such echoes would be extremely hard to detect, buried in noise and nearly invisible to current instruments. Yet if they exist, they would carry precious clues about the stuff lurking just outside, or perhaps even within, the black hole. Several research teams have already searched for hints of these echoes in the data. So far, the results are mixed. Some analyses claim possible evidence, while others argue that the signals are statistical flukes. Nothing is yet certain. But the very possibility is enough to ignite excitement, because if echoes are real, they would mean that black holes are far stranger than we ever imagined. Even without echoes, gravitational waves already tell us more than we once thought possible. When a black hole merger occurs, the gravitational pull of the system changes in ways that ripple outward. These ripples do not directly carry matter from the inside, but they reflect how the whole structure moves, shifts, and deforms. Studying them is like watching the surface of a drum. You cannot see inside the drum, but the way the skin vibrates reveals whether it is stretched tight, how deep the drum might be, and perhaps even whether something is rattling inside. Black holes are the same. By reading the waves they release, we can infer secrets that lie close to or even just beneath their horizons. Gravitational waves also arrive in a sequence, not as a single burst. Some parts of the wave travel differently, depending on how space is warped near the black hole. This means that tiny delays, subtle shifts, and delicate changes in the wave pattern encode information about the black hole's structure. Decoding these whispers is difficult, but the rewards could be immense. Right now, our knowledge is basic. With current technology, we can tell when a black hole merger happens, estimate the masses of the objects involved, and measure some features of the final black hole. But the dream is much bigger. With more data, sharper instruments, and better models, we may one day build a catalogue of black hole voices. Each collision would be like a performance, each ringdown like a unique tone resonating across the universe. And just as human voices carry hints of emotion, history, or health, these cosmic voices might carry hints of the hidden nature of each black hole. Imagine for a moment the most mysterious objects in the universe, black holes, the cosmic traps from which nothing, not even light, can escape. For decades they have been described as bottomless pits, regions of space where matter is swallowed forever, crushed to an infinitely small point. But what if these terrifying objects are not just dead ends? What if, hidden within them, lies something far stranger and perhaps far more useful than anyone first imagined? Some scientists have asked a bold question. Could black holes actually be wormholes in disguise, secret passageways to other parts of the universe, or perhaps even to other universes entirely? To understand this idea, picture space itself not as an endless void, but as something that can bend and stretch, almost like a sheet of paper. If you draw two dots far apart on the paper, the only way to move from one dot to the other is to travel across the surface. But if you fold the paper so that the dots overlap, then punching a hole through allows you to move instantly from one point to the other. This is the basic idea of a wormhole, a shortcut through the fabric of reality. Instead of crossing billions of miles of space the long way around, you jump through a tunnel that connects distant regions directly. The concept is beautiful, but reality, as always, is more complicated. The equations that first described wormholes suggested they would collapse too quickly to be useful. Imagine trying to crawl through a tunnel only to have the walls close in before you even make it halfway. The opening pinches shut almost immediately, leaving no chance for a traveller, a particle, or even a photon of light to pass through. For many years, this seemed to doom the dream of wormholes. But later, theorists found a possible loophole. If, in some way, the throat of the wormhole could be propped open with a kind of strange material, something with negative energy that pushes outward rather than pulling inward, then the tunnel might remain stable long enough to be crossed. This is not ordinary matter. It is exotic, unlike anything we see in daily life. But quantum physics does suggest that, at least in theory, such negative energy can exist. And if it can exist, then wormholes might not be impossible after all. What makes this even more intriguing is that, from the outside, a wormhole could look almost exactly like a black hole. Both would bend light in dramatic ways. Both would appear to have a boundary that nothing escapes from, a kind of event horizon. Both would cast similar shadows when surrounded by glowing gas and dust. To a distant observer, the two might be indistinguishable, yet what happens inside could be radically different. Falling into a black hole means being torn apart by gravity and crushed into oblivion. Falling into a wormhole, on the other hand, could mean emerging somewhere else entirely, perhaps on the far side of the galaxy, perhaps in another galaxy altogether, or if some of the bolder theories are correct, perhaps in another universe beyond our own. The difficulty is telling the difference between these two cosmic phenomena. Scientists suggest that wormholes might reveal themselves in subtle, almost ghostly ways. For example, when something falls into a black hole, it disappears forever beyond the event horizon. But if it falls into a wormhole, the process might produce strange signatures, unusual flashes of radiation, delayed jets of matter, or gravitational tugs from something on the other side of the tunnel. Wormholes might even create a kind of echo, ripples of energy bouncing back and forth through the tunnel before fading away. These repeated ringing patterns would be unlike anything produced by an ordinary black hole. Detecting such faint signals would be incredibly difficult, but not impossible. Modern physics has even linked the idea of wormholes to the strangest feature of the quantum world: entanglement. Entangled particles behave like twins, perfectly connected no matter how far apart they are. Some researchers now suggest that entangled particles may actually be linked by tiny wormholes, invisible bridges threading through space. This idea is sometimes expressed by the phrase ER equals EPR, connecting Einstein and Rosen's concept of wormholes with Einstein, Podolsky, and Rosen's description of entanglement. If this interpretation is true, then wormholes are not just rare cosmic oddities, but the fundamental glue of reality itself. Every entangled pair might hide a microscopic wormhole, and larger wormholes might be woven together from countless such connections. If wormholes can connect different regions of our universe, that is already staggering. But if they can connect different universes, the implications are even greater. A black hole in our own cosmos could serve as a doorway to a parallel reality, a universe with its own laws of physics, its own particles, even its own dimensions. Matter falling into such a black hole would not be destroyed, it would simply be transferred, emerging in a place entirely beyond our reach. Such wormholes would act as cosmic transport stations, linking worlds that would otherwise remain forever separate. The obvious question is whether we could ever travel through one ourselves. The answer is not clear. Some wormholes, if they exist, might be unimaginably small, tinier than an atom, far too small for a spacecraft or even a single particle of dust to pass through. Others might be large enough to see with the naked eye, or perhaps vast enough to swallow stars, but unstable, collapsing before they could be crossed. Even if a stable wormhole large enough for human travel were discovered, the journey would be unimaginably dangerous. The forces inside could stretch and tear apart any traveller. Radiation and energy fields might be lethal, and the engineering challenge of finding, stabilizing and navigating such a portal would dwarf anything humanity has ever attempted. Yet the possibility cannot be dismissed entirely. If even one natural wormhole exists and can be kept open, it would represent the greatest discovery in history, the first real gateway beyond the limits of our universe. But how could we ever prove that a black hole is secretly a wormhole? The challenge is that black holes hide everything beneath their event horizons. Not even light escapes to tell us what lies within. Even the famous image of the black hole in the galaxy Messier 87, captured by the Event Horizon Telescope, shows only the glowing outline of gas swirling around the darkness. We do not see the interior. We cannot peek inside to check whether a tunnel stretches beyond. Instead, scientists rely on indirect methods. They build simulations and mathematical models, trying to predict how a wormhole would behave compared to a black hole. Then they search the sky for signs that do not fit the black hole picture. A flicker where none should exist, a second echo in the gravitational waves, a delayed burst of radiation that seems to whisper of something more. These subtle mismatches, if found, could provide the first hints that wormholes are real. And so, the darkest objects in the universe, once feared as symbols of destruction and finality, may instead turn out to be doors. Hidden within the shadows we thought were traps could lie pathways, tunnels through reality itself. If one day we discover how to unlock them, to step through or even send a signal across, then for the first time in human history, we would know what lies beyond the edge of the known world. The idea that black holes might be wormholes in disguise is not just science fiction. It is a daring possibility, born from the mathematics of relativity, nurtured by the strangeness of quantum physics, and pursued by the most curious minds of our age. Whether it turns out to be true or not, the search itself reveals something profound, that we live in a universe filled not only with mysteries but with hidden possibilities, waiting for us to unfold them. Falling into a black hole is one of those ideas that both terrifies and fascinates people at the same time. On the surface, it sounds like a direct and irreversible path to destruction, and for many black holes, that is exactly what it would be. If you were unlucky enough to fall into a small black hole, the kind with only a few times the mass of our Sun, you would never make it anywhere close to its centre. The gravitational forces would rip you apart long before you ever reach the event horizon, the invisible boundary that marks the point of no return. These forces are called tidal forces, and they stretch objects in one direction while squeezing them in another. In this case, your body would be pulled into a long, thin shape, a process scientists grimly call spaghettification. It would be quick, violent, and inescapable. But things change when you consider a much larger black hole, one of the monsters we call supermassive black holes. These giants are not just a few times bigger than our Sun, they can weigh millions or even billions of times as much. Their gravitational pull is far stronger overall, Yet surprisingly, the experience of falling into one could be very different. This is because the way gravity behaves near their event horizon is not as extreme as in smaller black holes. The curvature of space and time changes much more gently near the edges of a supermassive black hole, which means that the difference in gravity between your head and your feet would not be as drastic. In other words, the tidal forces are weaker at the horizon of such a giant. That opens the possibility that, at least in theory, you could cross over the event horizon of a supermassive black hole without even realizing it in the moment. There would be no jolt, no obvious line in space that you could point to and say, "This is it." You would simply drift past, feeling as though nothing unusual had happened. Yet that silence, that lack of warning, would be its own kind of horror. Because once you are past that invisible boundary, no message, no light, no radio signal, no scream could ever travel back to the outside world. If you wanted to tell anyone what you were experiencing, your very last chance would be just before crossing over, when you could still send out a signal. Beyond that moment, you would vanish from the universe's stage, cut off forever. So what would it actually feel like to fall into one of these giants? Imagine starting your journey from a safe distance away, where the black hole is still just another dot in the sky. Slowly, though, its pull would begin to dominate. You would accelerate gently at first, then faster and faster, dragged ever closer by its gravity. The stars behind you would not stay still. Because of the powerful effects of gravity on light, the starlight might begin to stretch and warp in strange ways, a phenomenon known as gravitational lensing. The black hole itself would not look like a traditional hole. Instead, it would appear as a perfectly dark circle, almost like a cosmic void, surrounded by a glowing halo of light. This halo would be formed from the disk of superheated gas and dust spinning furiously around it, material caught in a deadly whirlpool as it spirals inward. As you drifted closer, the light from stars behind the black hole would bend and smear around its edges. The universe itself would begin to look warped, as if you were peering through a twisted lens. The sky might seem to swirl and stretch, with shapes and patterns that made little sense to human eyes. Time itself would play tricks on you. From your perspective, everything would seem normal. You would experience seconds and minutes just as you always had. But if you could somehow look back at the outside universe, it would be a different story. To you, the outside world would appear to be moving faster and faster, galaxies racing through time, stars aging in moments, light from distant places shifting into deeper and deeper shades of red until it faded away altogether. The universe would appear to compress itself into a single fading glow until only darkness remained. Crossing the event horizon itself would not be a dramatic event. It is not a physical wall or a visible surface, but simply a boundary in space where escape becomes impossible because the speed required to break free would have to exceed the speed of light. To an outside observer, it would look as if you froze right at the horizon, your image stretched and reddened until it faded away. But from your point of view, you would simply keep going. One moment you were outside, the next you were in, and you would feel no sudden change. Ahead of you would be deeper blackness. Behind you, a vanishing memory of the universe you once knew. Once you're inside, your fate depends on the true nature of the singularity, the mysterious heart of the black hole. In the traditional models of physics, the singularity is a point of infinite density, a place where space and time are crushed to nothing and where all paths lead inward. Once you're inside the horizon, there is no escape, no way to fight your way back. No matter what you do, you're drawn toward that center, pulled along by the unavoidable flow of space and time itself. But not all scientists are satisfied with that explanation. Some theories suggest that quantum mechanics, the strange set of rules that govern particles on the smallest scales, might change the story. Instead of a perfect point, the singularity could be smeared out into a different kind of core, something that does not instantly obliterate everything that touches it. If that is true, then falling into a black hole might not mean instant destruction after all. Your journey could last longer, perhaps much longer. You might drift deeper into warped regions of space, passing through areas where distance and direction lose their ordinary meaning. The very structure of reality would bend and twist around you. Perhaps you would float through curved pockets of space-time, witnessing sights unlike anything in the outside universe. In the end, you might still be destroyed, but the process could be slow, complex, and filled with strange wonders along the way. Some physicists have even speculated that black holes might act as time machines of a sort. Because of the way time stretches near the event horizon, someone falling in might be able to witness the future of the universe unfold in front of their eyes. From your perspective, the outside cosmos could speed forward by millions or even billions of years, while you experienced only a few minutes. You could watch galaxies drift apart as the universe expands, stars burn through their fuel and die, new generations of stars form, and civilizations perhaps rise and fall. What would take eons outside might pass before you like a sped-up movie. So while the classic picture of falling into a black hole is one of instant death, being shredded and crushed, the truth is not so simple. If the black hole is small, yes, you would be torn apart almost immediately. But if it is a supermassive one, the story is different. You might have minutes, hours, or even longer before you reach the central region where things become truly deadly. Those final moments could be strangely quiet, even beautiful in a haunting way. You might experience the eerie calm of a world without escape, a place where the laws of physics themselves seem to blur and bend. It could be a journey not just of terror but also of awe as you drift through the edge of human understanding, watching the universe fade away while stepping into the deepest mysteries of existence. In quantum physics, especially the branch called quantum field theory, the strange idea of negative energy pops up now and then. It does not act like the familiar energy that always adds to a system. Instead, negative energy can take away. Imagine energy that subtracts rather than adds. Normally, the gravity of a black hole grows stronger and stronger, bending space and time so that every possible route leads inward toward the center. But suppose you had some way to push back against that bend. What if, instead of being yanked inward and pulled into long, thin threads, you could smooth out the pull? That is where negative energy enters the story. In theory, if you wrapped yourself in a field of negative energy, it could behave like a cushion or a soft bubble. As the black hole's gravity tightened, the negative energy could cancel some of that pull. Instead of being stretched into spaghetti or crushed flat, you might feel no strong tug at all. You could float, almost as if gravity around you were reduced or even reversed. It is a strange idea, a kind of reverse gravity acting like a local pacifier against the black hole's violence. Physicists sometimes call the stuff that would carry negative energy exotic matter. It would not be made of atoms like ordinary matter. It would obey odd rules. It could have negative pressure or a negative energy density. Phrases that sound technical but simply mean the material behaves opposite to what we're used to. These properties are what would let it counteract normal gravity. One real laboratory effect that physicists mention when they talk about negative energy is the Casimir effect. If you take two extremely thin metal plates and put them very, very close together in a perfect vacuum, a place with almost no particles, quantum jitters in the vacuum make the energy between the plates slightly lower than the energy outside. That tiny deficit acts mathematically like a small amount of negative energy. It's not a dramatic spaceship protecting force. It's a tiny, delicate effect that only shows up on atomic scales and must be measured with precise instruments. Still, it proves that empty space isn't always boring. Under special conditions, the quantum vacuum can behave in ways that surprised even the people who discovered it. So, if negative energy is not just a mathematical toy but can really exist in some form, could we use it to explore or survive a black hole? Right now, the hard truth is no. We cannot make large amounts of negative energy, and we certainly cannot shape it into a steady, protective bubble. The Casimir effect acts only over extremely small distances. To shield a spaceship, a person, or even a tiny probe, you would need a field that stretches across kilometers, and you would also need to hold that field steady. Negative energy, as far as current theory suggests, is fussy. It flickers and moves around like a candle flame in a breeze. It does not behave calmly and predictably. To harness it would require technology so far beyond ours that it might as well be called magic. Some thinkers have tried to imagine clever ways around those limits. Rather than using negative energy as a direct shield, perhaps you could use it to reshape space itself. This is the route taken by ideas like wormholes and warp drives. Instead of fighting gravity head-on, you would bend the road ahead so the dangerous region no longer lies on your path. Picture space-time as a landscape. Instead of climbing a deadly waterfall, You sculpt a tunnel that carries you safely beneath it. That kind of trick would still need large amounts of negative energy according to general relativity, far more than we know how to produce. Many researchers argue that even if you could gather enough, quantum effects would likely make your tunnel or bubble collapse almost at once. Nature may introduce checks that prevent those constructions from lasting. Still, some scientists propose that negative energy might not be so rare. Short-lived pockets of negative energy might appear naturally in violent places, near black holes during intense particle collisions, or in other extreme corners of the cosmos. If pockets like that do form, they might influence how a black hole behaves for a brief moment. Perhaps they nudge the event horizon in subtle ways, or they have a tiny role in phenomena like Hawking radiation. Or maybe they just appear and vanish too quickly for us to notice. The possibility that negative energy sneaks into play in natural settings keeps the door open to further thinking and experiment. Let's imagine a very advanced civilization, one that is thousands or even millions of years beyond us. Suppose such beings discovered how to trap and control negative energy. In theory, with that mastery they could wrap their ships in protective fields that cancel out the worst tidal forces near a black hole. Their explorers might dive through an event horizon as casually as we dive into the ocean. Instead of being shredded, they could coast into the unknown, guided by their machines. Inside a black hole, a skilled use of negative energy might serve another purpose: steering. If space-time is twisted into wild shapes, a controlled field of negative energy could act like a rudder or fin, making fine course corrections. Rather than falling helplessly toward the singularity, an explorer might aim for a particular target: a stable pocket, the throat of a wormhole, or even an exit leading somewhere else. In that universe of possibility, falling into a black hole would not necessarily mean being trapped forever. It could become a route to another region of space, or another universe entirely. Of course, none of this is engineering reality today. No one has built a negative energy generator. No one has tested an exotic matter shield. It is possible the fundamental laws of physics forbid sustained, large-scale negative energy precisely because it would enable paradoxes or violate deeper rules. Even so, asking the question is useful. Exploring these ideas pushes us to probe the edges of physics, to poke at the equations and see what they hide. Negative energy sits at one of those edges. It suggests that the vacuum itself, the fabric of space-time, might hold secrets, subtle mechanisms that link gravity and quantum fields in ways we have only begun to glimpse. If, someday, we could learn to control negative energy, the prize would be enormous. We would not only gain a way to approach and study black holes safely, we might also learn to shape the deeper geometry of the universe. For now, negative energy remains a hint, a whispered possibility from the math and a handful of delicate experiments, a reminder that empty space may be richer and stranger than it appears. String theory puts forward a bold and fascinating idea, that the tiniest building blocks of the universe are not particles at all, but unimaginably small strings. These strings are far, far smaller than atoms, and even tinier than the particles that make up atoms, such as electrons and quarks. To get a sense of scale, if an atom was stretched to the size of our entire solar system, a string would still be no bigger than the size of a tree. That is how small these fundamental threads are supposed to be. And these strings are not motionless. They are alive with movement, always trembling and vibrating, much like the strings of a violin or a guitar. Just as the way you pluck or bow a musical string creates a specific note, the way these cosmic strings vibrate decides what kind of particle they become. One type of vibration might produce a photon, which carries light. Another vibration could create an electron, which forms the backbone of chemistry. Yet another might produce a quark, one of the essential ingredients of protons and neutrons. This picture changes the way we think about the foundations of nature. Instead of imagining particles as tiny dots with no size, string theory asks us to picture them as tiny loops or strands of vibrating energy. And although this sounds like a small change in perspective, it could completely alter how we understand extreme places in the universe, such as black holes. In ordinary physics, a black hole is thought to crush everything that falls into it, down to a single point of infinite density, known as the singularity. But if particles are not dots and are instead strings, then perhaps they cannot be crushed into a point at all. Instead of collapsing into nothingness, the strings might stretch, smear, and tangle together. Rather than forming a singularity, They might create a fuzzy, tangled ball of vibrating threads. This idea is sometimes called the Fuzzball model of black holes. In this model, the inside of a black hole is not a smooth and empty pit, but a chaotic, densely packed cloud of tangled strings. The event horizon, the invisible boundary that marks the point of no return, may still exist. If you cross it, you can never escape. But what lies beyond is not a singularity in the usual sense. Instead, it is a kind of stormy ocean of strings, all vibrating, colliding, and twisting in wild ways under the immense pull of gravity. The black hole remains just as deadly, because the gravitational forces near it are still unimaginably strong. But the rules of how matter, space, and time behave inside could be very different from the predictions of Einstein's theory of general relativity. Some strings, according to the theory, might even stretch into dimensions that we do not normally see. In our everyday lives, we experience 3 dimensions of space: length, width, and height, along with 1 dimension of time. But string theory suggests there could be additional hidden dimensions curled up so tightly that we cannot perceive them. These extra dimensions could fold and twist within the fabric of space itself, perhaps wrapping up into intricate tiny shapes known as Calabi-Yau spaces. If such dimensions are real, then the interior of a black hole might not simply be 3-dimensional. Instead, it could be a vast, multi-dimensional network woven out of the strings themselves. One of the remarkable features of strings is that they are not static. Strings can split apart and then rejoin. They can carry energy, momentum, and electric charge. And in certain versions of the theory, strings can also grow into higher dimensional objects called branes. A brane is like a stretched out version of a string, not just a 1-dimensional line, but a 2-dimensional surface, or even a 3-dimensional volume. Some versions of string theory even propose that our entire universe might itself be a brane, floating like a sheet within a higher dimensional space. This raises intriguing questions about what happens when strings and branes fall into a black hole. Do they vanish forever, swallowed whole, or do they leave behind a trace of their existence? One suggestion is that strings might leave an imprint on the black hole's surface as they cross the event horizon. This idea is tied to something called the holographic principle, which is one of the most exciting insights to come from string theory. According to this principle, everything that happens inside a region of space, such as the inside of a black hole, can be described by information written on its boundary. It is as if the universe itself is like a giant hologram, where a 2-dimensional surface holds all the information needed to describe a 3-dimensional interior. This idea appears in what physicists call the ADES CFT correspondence. On one side of this correspondence is a universe filled with strings, black holes, and curved space-time. On the other side is a world described entirely by quantum fields, the same language scientists use in laboratories to describe the behavior of particles. The strange and beautiful part is that the 2 descriptions are completely equivalent, like 2 different maps that describe the same landscape. Some physicists have gone even further, suggesting that space itself, the very thing we move through and live inside, is built out of the connections between strings. If that is true, then the inside of a black hole is not just a location in space. It is a structure, a tightly woven fabric made from the way strings interconnect. Gravity, time, and motion might not be fundamental forces at all, but rather side effects of the way strings interact. In this picture, the singularity at the center of a black hole could be nothing more than an illusion. General relativity predicts it only because it treats the universe as smooth and continuous. But if we zoom in beyond atoms, beyond protons, down to the level of strings, the universe is not smooth at all. It is a vibrating, knotted web of strands stretching into hidden dimensions. What we thought was a singularity is really just a misunderstanding of the deeper structure. Another fascinating possibility from string theory is that black holes may not be entirely black. In the usual picture, Hawking radiation explains how black holes can slowly lose energy by allowing particles to tunnel out of empty space near the horizon. But if particles are strings, then perhaps they can wiggle in such a way that some of their energy leaks out directly. This would offer a new way to explain Hawking radiation, not just as particles popping out of the void, but as the restless song of strings echoing beyond the event horizon. Despite all these thrilling ideas, it is important to remember that string theory remains unproven. Its equations are elegant, sweeping, and full of promise, but they are very difficult to test with experiments. We do not yet have the tools to directly detect strings or to probe the hidden dimensions they require. Still, string theory gives us a way to imagine the universe in an entirely new light. Instead of seeing black holes as terrifying voids with a crushing singularity at their heart, we might picture them as cosmic knots, dense, tangled, vibrating clusters of strings tied together in mysterious ways. They are no less dangerous, but their mystery is richer and more intricate than we once thought. If this view is correct, then the universe itself may be a kind of grand symphony. Black holes are not silent pits of destruction, but rather tangled songs of strings, humming and vibrating in dimensions just beyond our sight. The singularity is not an end, but a veil hiding a deeper and more beautiful structure, a hidden harmony woven into the very fabric of reality. For over a century, scientists have wrestled with the strange and mysterious nature of black holes. According to the traditional picture, a black hole forms when gravity becomes so strong that nothing, not even light, can escape. Albert Einstein's theory of general relativity, published in the year 1915, describes this process with incredible precision. Yet, when gravity pushes matter to its ultimate extreme, Einstein's theory predicts the formation of a singularity, a place where space and time collapse into an infinitely small point and the known laws of physics break down. This is where physicists know something is missing in the picture, and many competing theories have been suggested to fill the gap. One of the most fascinating of these ideas comes not from string theory, but from another approach called loop quantum gravity. Loop quantum gravity, often shortened to LQG, is a bold attempt to merge the strange rules of quantum mechanics with the smooth curves of general relativity. Instead of treating space as a continuous fabric that can be stretched and bent without limit, LQG proposes that space itself is woven out of unimaginably tiny loops. You can imagine it like a cloth. From a distance, a piece of fabric looks smooth and unbroken, but if you place it under a microscope, you will see threads woven together. Loop quantum gravity says that space is like that. At very small scales, it is built out of loops of energy, and these loops give space a kind of grainy texture. When gravity becomes extremely strong, such as inside a black hole, general relativity predicts that nothing can stop the collapse. Matter falls inward without end until it is squeezed into a point of infinite density. But loop quantum gravity tells a different story. At the smallest scales, the loops that make up space resist being compressed beyond a certain limit. They act almost like the coils of a spring. If you push a spring too far, it pushes back with growing force. Similarly, the loops in space push back against gravity, preventing it from crushing everything into a singularity. This means that the collapse of a star into a black hole does not end in a dead end of infinite density, but instead in a kind of bounce. Matter rushes inward, compressing tighter and tighter until the loops resist any further collapse. Then, just as a compressed spring rebounds, the dense core of the black hole begins to expand again. What was once a crushing collapse turns into an explosion of rebirth. Inside the black hole, space may expand into a new universe of its own. This idea is revolutionary because it does not rely on strange, exotic forms of matter or undiscovered particles. Instead, it comes naturally from rewriting gravity itself to include quantum effects, something Einstein's general relativity does not do. In this way, loop quantum gravity provides an answer to one of the most troubling questions in modern physics. What happens at the heart of a black hole? This picture is very different from the Fuzzball proposal that arises from string theory. In the Fuzzball model, black holes have no interior at all. According to this view, all of the mass and energy of the black hole are stored in tangled strings near the surface. Space does not continue inside, and nothing ever gets through. Time itself seems to stop at the horizon. You could say that in the Fuzzball world, the black hole is like a tightly packed tangle with no room inside, and the story ends at the surface. Loop quantum gravity paints a more dramatic image. In this theory, there is indeed an inside to a black hole. Space and time continue to exist within, and as matter falls inward, the structure of loops allows a compressed core to form. This core is not a singular point, but rather an unimaginably dense knot of loops. From this compressed state, something entirely new may emerge, the birth of another universe. One of the most fascinating differences between the Fuzzball picture and the bounce picture is their treatment of time. In the Fuzzball model, time halts at the edge of the black hole. There is no after, because there is no inside. But in loop quantum gravity's bounce scenario, time does not stop. The collapse of matter does not freeze into a singularity. Instead, the future continues in a different form. The falling matter is reborn in a new beginning, a new expansion, perhaps even a new cosmos with its own stars, galaxies, and maybe even life. This idea also offers a fresh way of thinking about the infamous information paradox, one of the greatest puzzles of black hole physics. According to Stephen Hawking's work in the 1970s, black holes slowly evaporate by giving off a faint glow of radiation, known today as Hawking radiation. But this process seemed to destroy information about what fell into the black hole, something that clashed with the basic principles of quantum mechanics. In the Fuzzball model, the information is stored in the tangled structure of strings at the surface of the black hole, and then slowly leaks out as radiation. In the bounce model, however, the story is different. The information does not vanish, and it does not merely leak back into our universe. Instead, it may travel through the bounce into the new universe that forms inside. In that case, the information is preserved, but hidden forever behind a kind of cosmic curtain, no longer accessible to us. This leads to breathtaking speculation. What if our own universe was born from the collapse of a black hole in some other parent universe? In that case, the faint background glow of radiation that fills our sky, known as the cosmic microwave background, might carry tiny fingerprints of its origin. Physicists have suggested that unusual circles or subtle patterns in this ancient light could be signs of such a cosmic bounce. Although no conclusive evidence has yet been found, researchers continue to search. The bounce idea also changes how we think about the lifespan of black holes. In the traditional view, black holes slowly shrink over unimaginably long timescales, evaporating into nothing. But loop quantum gravity suggests that when a black hole reaches the quantum stage, it could suddenly transform rather than fade away. To an outside observer, it might appear as though the black hole simply vanishes, replaced by a strange burst of energy. That burst could be the last spark of connection between two universes, or it could mark the very instant when a new universe is born. Some versions of the theory even hint that the interior of a black hole is not completely cut off from our universe. There could be subtle mathematical links, delicate threads connecting the two sides. If such links exist, they might allow faint traces of communication or influence between universes, though in ways far beyond our current understanding. Though these ideas live at the edge of speculation, they are not idle fantasies. They drive physicists to look deeper into the structure of space and time, to build experiments, to refine mathematics, and to test what might otherwise remain unknowable. Whether or not loop quantum gravity ultimately proves correct, it offers a powerful reminder that the universe may be far more creative and surprising than we imagine. Time inside a black hole is one of the most puzzling and haunting mysteries in science. It raises questions that stretch beyond physics into philosophy itself. Does the future already exist? If so, are we simply moving through it as if it were already written? We already know from Einstein's theory of relativity that black holes bend and stretch time itself. The closer you get to one, the more the flow of time is twisted. But what exactly happens to time once you pass the event horizon and sink deeper toward the singularity? No one truly knows, but theories paint images that are both astonishing and unsettling. From the viewpoint of someone falling into a black hole, time outside might appear to race ahead at unimaginable speed. What seems to us on the outside like billions of years could, for the falling traveller, pass in what feels like the blink of an eye. Galaxies could rise and fall, stars could flare and explode, even the universe itself could age to its very end, all while the traveller is still plunging inward. In this strange vision, falling into a black hole could be like pressing fast forward on the history of everything. Some scientists go further and suggest that inside a black hole, the future is not something waiting ahead like a road yet to be travelled. It is already there. This idea comes from a concept in general relativity often called the block universe. In this view, space and time are not flowing like a river, but are instead frozen into a four-dimensional structure. Imagine the entire history of the universe as a giant book. Every page is already written, the past, the present, and the future. You may only read one page at a time, but all the pages exist together in the same volume. To you, the future feels like something you approach, but to the universe, it is already there, waiting. Inside a black hole, this block universe picture might stop being a theory and become a reality. The extreme warping of space and time could force every traveller toward a fixed ending, a moment in the future that already exists and cannot be avoided. Crossing the event horizon may be like stepping onto a conveyor belt you cannot escape. Every step you take, every second that passes, no matter what you do, even if you stand perfectly still, carries you closer to that inevitable point. This raises deep and unsettling questions about free will. If time is just another direction, like north or south, and you're sliding down it without the ability to stop or turn, are you really making choices? Or are you simply acting out a script already written by the geometry of the universe? Some physicists argue that this is not unique to black holes at all, that perhaps the entire cosmos works this way, with the past, present and future existing together, and our sense of freedom being just an illusion. But black holes make this possibility impossible to ignore, because inside them the drag of time is not abstract. It becomes a physical force that pulls you relentlessly to a destination that exists before you even arrive. And yet, quantum mechanics complicates this picture. In the strange world of quantum theory, particles do not follow single fixed paths. They explore all possible routes at once until a measurement is made. Some scientists hope that a true theory of quantum gravity, the long-sought unification of Einstein's relativity with quantum mechanics, might rescue us from the bleak idea of a fixed fate inside black holes. Perhaps the singularity is not truly the end. Perhaps quantum effects allow you to bypass it, skip over it, or dissolve it entirely. Until such a theory is complete, however, we are left with an eerie vision. The singularity at the centre of a black hole, not just as a destination but as a waiting moment, silent and unavoidable, a marker on the road of existence that already knows you are coming. But what if black holes are not just ends but also beginnings? Some theories suggest that they may be connected to their opposites, white holes. If that is true, then time inside a black hole might reverse. What looks like an ending to us could, from another perspective, be a birth. The singularity would no longer be a grave but a tunnel where time restarts, flowing in the opposite direction. In this vision, the universe does not end once it collapses. Instead, collapse becomes expansion. Death becomes rebirth, and the future becomes part of a grand loop, a cycle of falling in and bursting out, of compression and release. Whole universes could be linked together in this strange chain of tunnels, with black holes serving as doorways from one to another. This leads to an even more unsettling question. What if we ourselves are already inside such a black hole? If that is the case, why do we not notice it? Why do the skies not collapse around us? Why does the universe not appear to be folding inward? One answer is that the event horizon is too far away to see. Imagine living inside a vast balloon. From your point of view inside, the space looks endless and flat. You cannot see the balloon's curved surface because it is far beyond your reach, but from the outside, your entire world is enclosed, hidden by that boundary. If our universe is the inside of a cosmic black hole, we may never notice because we can never step outside to compare. Inside a black hole, the very geometry of space and time shifts. Distances warp, directions twist, and time becomes inseparably tied to motion. Sitting still moves you closer to the singularity. Doing nothing still carries you along. Every action is part of the fall. If you stretch this concept to the larger scale, it begins to sound very much like the story of our universe. We often think of the Big Bang, which happened about 13.8 billion years ago, as the beginning of time itself. But from another perspective, the Big Bang could resemble the singularity at the heart of a black hole. In that case, the singularity is not behind us, but is what we emerged from. Our universe could be the interior of some colossal collapse, now expanding outward. But why then can we not escape our universe if it is indeed the inside of a black hole? The answer may be that escape simply has no meaning here. The universe is not expanding into some greater space, it is expanding within itself. Space itself is stretching, galaxies are moving apart, yet the whole thing may still be shaped by an invisible horizon, a cosmic boundary that we can never see because it is not outside of us but all around us, lying forever beyond what we can observe. Just as nothing inside a black hole can reach the outside, nothing inside our universe can ever reach beyond its cosmic horizon. What makes this even more fascinating is that space inside a black hole can feel surprisingly normal. If you fell into a supermassive black hole, larger than millions of suns, you might experience a vast, open interior, and even a sense of floating weightlessness before your fate finally caught up with you. The bigger the black hole, the gentler the ride, at least for a while. If the universe itself is the interior of such a black hole, then it would be the largest possible one, so enormous that its curvature feels invisible to us. The event horizon could be billions of light years away, perhaps farther. From our perspective, space looks ordinary, but from another, we are deep inside something massive, curved, and inescapable. Some physicists have taken the mathematics of black holes and applied it to the universe as a whole. Strangely enough, under certain conditions, the interior of a black hole can look exactly like a universe, with galaxies, stars, light, and laws of physics all unfolding within it. If so, it could explain why our cosmos looks the same in every direction, and why there is no clear trace of what came before the Big Bang. If the Big Bang was really just the birth of a space-time bubble, then we are living inside it and always have been. The horizon is not something far away we can fly toward. It is baked into the geometry of everything around us. Perhaps we are already beyond the point of no return. Some scientists go even further and propose that universes can split apart entirely. If a universe inside a black hole expands quickly enough, it might eventually disconnect from its parent completely. The tunnel linking it, the black hole's throat, could collapse and seal shut. At that moment, the two universes would become entirely separate with no bridge between them. In theoretical physics, these are sometimes called baby universes. A baby universe might begin as a tiny fluctuation, grow, and then break free, drifting away with its own time, its own stars, its own laws. For this to work, however, expansion must outrun gravity in a dramatic way. If it does not, the baby universe will collapse back into the singularity, never reaching maturity. But if expansion succeeds, the new universe can grow endlessly, forever out of reach of the parent. If this is true, then maybe we ourselves are such a baby universe. Perhaps we began inside the collapse of something else, but our inflation carried us beyond the reach of that parent black hole. If so, then we are already free. We're no longer bound by our beginning. We're expanding into our own future, into a cosmos that may never know exactly where it started. Still, the mystery refuses to end. Could this be happening right now, inside black holes scattered across our night sky? Could countless universes be forming even as we watch, each with its own galaxies, its own stars, its own questions? And in those other universes, might there be beings wondering the same things we are, asking if they too were born from something else, and if they too have already escaped? Imagine for a moment that the universe hides secrets behind walls that aren't really walls. In our ordinary world, if you throw a ball at a wall, it bounces back. That is how we expect things to behave. But in the strange world of quantum physics, the rules are not so simple. If you throw an electron at a wall, there is a tiny chance that instead of bouncing back, it will vanish from one side and suddenly reappear on the other, as if the wall had never been there at all. It doesn't climb over the wall, it doesn't sneak around it, it doesn't smash through, it simply appears on the far side, skipping the middle altogether. This bizarre trick is called quantum tunneling. Now, imagine taking that strange idea and applying it to one of the most mysterious objects in the cosmos, the black hole. At first glance, a black hole seems like a perfect prison. The event horizon, the boundary around it, marks the point of no return. Cross it, and you are trapped forever. But what if that boundary isn't as absolute as we think? What if, at the quantum level, particles can tunnel through it, moving both inward and outward, slipping past the rules that classical physics has set in stone? If tunneling is possible near the event horizon, then the interior of a black hole might not be the silent, sealed-off chamber we once imagined. Instead, it could be alive with hidden traffic. Particles that should be imprisoned forever could sometimes escape. Meanwhile, particles from outside, tiny, fleeting quantum visitors known as virtual particles, which flicker in and out of existence, might find their way in. This would mean that the inside of a black hole is not completely cut off. It is, in a subtle but very real sense, still connected to the rest of the universe. Some physicists go even further. They suggest that the interior of a black hole might not be a single simple space at all, but a place with layers, like the layers of an onion. Each layer could be a quantum state with its own density, energy, and structure of space and time. Imagine overlapping realities stacked inside each other. To our classical minds, they would be unreachable, locked behind walls of gravity. but through tunneling, particles, or even pure information might slip from one layer to another, crossing barriers that should be impassable. In this picture, the inside of a black hole becomes a maze of quantum zones, some stable, some constantly shifting, all invisible from the outside. To grasp how this could work, we need to return to the idea of barriers in quantum mechanics. In our everyday world, a barrier is solid, a wall, a fence, a locked door. But in quantum physics, a barrier is any region where the rules of energy say, you should not pass. Yet because particles are also waves, the impossible sometimes becomes possible. A wave can seep into the forbidden zone, and if the conditions are right, if the barrier is thin enough or the energy is just so, the particle can emerge on the far side. Inside a black hole, the situation is even more dramatic. Space and time are twisted beyond recognition. Gravity is overwhelming. Paths that might have been open in ordinary space become closed. Regions are cut off from each other. It looks like a perfect trap, but tunneling offers loopholes. A particle might vanish from one region and reappear in another, carving out hidden passageways through the geometry of space itself. This gives rise to a startling possibility: hidden interiors. If you fell into a black hole in the normal way, your path would lead straight toward the singularity, the final crushing end. But tunneling might provide sideways exits, paths that ordinary falling cannot reach. Perhaps the singularity is not the only destination. Maybe there are hidden regions nearby, filled with energy, with information, or even the seeds of entire new universes. They would remain invisible, cloaked by quantum barriers, but still present as part of the black hole's secret architecture. Some researchers attempt to describe these bizarre structures using advanced theories like string theory or loop quantum gravity. In these views, space-time itself is not smooth but foamy, jittery, alive with fluctuations. In such a restless environment, tunneling would not be rare. It might be a natural part of how the geometry of reality works. The interior of a black hole would no longer be a silent void, but a storm of overlapping quantum spaces, filled with bubbles, layers, and constant changes. Tunneling could be the hidden key that lets matter, energy, and information move through this storm. But this raises a profound question. What happens to the information carried by those particles? For decades, physicists argued about the so-called information paradox, the puzzle of whether black holes destroy the information that falls into them. If tunneling allows particles to move between quantum layers, then perhaps information is not destroyed. It might not escape completely into the wider universe, but it could survive, encoded in the folds and ripples of the quantum interior, preserved in a place we cannot see. If this is the case, then the old idea of falling smoothly into a singularity is far too simple. The interior of a black hole would not be a straight, doomed journey. It would be more like wandering through a quantum labyrinth, where the rules shift without warning, and shortcuts appear and vanish unpredictably. And there is an even more daring idea. Tunneling might not just explain the interiors of black holes, it could explain the birth of new universes. When matter collapses into a black hole, classical gravity says it should end at a singularity, a dead point where everything breaks down. But quantum mechanics tells us that when things shrink to such extremes, new possibilities open. Instead of stopping at a singularity, the collapsing matter might tunnel into a new region of spacetime. That new region could then expand, inflating into a baby universe of its own, hidden from ours but born through the quantum bridge of tunneling. This makes us ask, could our own universe have begun this way, emerging from the collapse of something else? Could every black hole in our cosmos be the doorway to another cosmos, endlessly branching, one universe giving birth to another through the invisible magic of quantum tunneling? And then there is the most unsettling twist, the role of observation itself. In quantum physics, the act of observing changes the system. Particles do not have fixed positions or speeds until they are measured. Until that moment, they exist as clouds of possibilities. But once observed, the possibilities collapse into reality. This is called the observer effect. Now imagine applying this to black holes. Without observers, a black hole is simply a region where space and time curve inward, where nothing can escape, where general relativity reigns supreme. But what happens when an observer falls in? Not by exerting force, but simply by being present as a conscious measuring entity. In quantum theory, even the possibility of interaction changes the system. That means the very presence of an observer could alter which quantum state the interior takes. Inside, the space might exist as a superposition of many possibilities, flat, curved, spinning, branching all at once. But the moment someone observes, that cloud of possibilities collapses. The black hole chooses one reality. In this sense, the shape of the interior might not even exist until it is observed. The observer effect, normally applied to tiny particles, could stretch to cover entire regions of space and time. This leads to mind-bending questions. Can two different observers experience two different black hole interiors, both correct in their own frames of reference? Physics has ideas like complementarity that allow for this possibility. But if both realities exist, which one is the real one? Or is reality itself layered, flexible, and shaped by the act of looking? If so, then black holes are not just cosmic traps or engines of destruction. They are laboratories where the deepest principles of the universe, gravity, quantum physics, information, and even observation come together. Inside them might be hidden doors, invisible layers, and entire new realities, waiting to be uncovered by the strange and unpredictable rules of the quantum world. The idea of complementarity tells us something unusual and almost unsettling. Perhaps there is no single fixed answer to what reality truly is. Reality itself might depend on the observer. Imagine not just people or machines watching black holes from far away, but actual observers falling into them, thinking, moving, and measuring as they go. Inside the black hole, the very structure of space and time might shift around such travellers, not in the sense of solid walls suddenly forming or tunnels opening like in some science fiction story, but in the deeper sense of quantum geometry itself bending and rearranging depending on what is being measured. Time inside might stretch and bend differently, depending on where and how you look. Events that once seemed fuzzy, wrapped in uncertainty, could suddenly snap into place the moment someone measures them. This idea does not come from fantasy alone. Some interpretations of quantum mechanics support exactly this way of thinking. Take the relational interpretation, for instance. It says that things like position, energy, or even momentum do not really exist on their own, floating independently. They only exist in relation to something else, most importantly in relation to an observer. If that is true, then the space inside a black hole is not an absolute thing at all. It would be defined by the relationships between everything inside and whoever is there to observe it. This would mean that every black hole interior could be unique, not just because of how the black hole itself was born, but also because of who or what enters it. Imagine two black holes that from the outside look exactly the same. Same mass, same spin, same electric charge. Yet if two different observers were to fall into them at different times, their journeys inside could unfold in completely different ways. Each would, in a sense, generate their own personal version of space-time, created right on the spot as they experienced it. Some theories go even further and propose something more radical. Space-time itself might not be a fixed background at all. Instead, it could be the result of quantum entanglement, the invisible connections that tie particles together across space. If this is true, then observing something does not just reveal what is already there. The act of observation helps create the very stage on which reality unfolds. And inside a black hole, where conditions are pushed to the extreme and everything is stripped down to its most basic level, this effect could become magnified. This would mean that the inside of a black hole is not sitting there waiting to be charted like a hidden cave. Instead, it is built through the very act of experiencing it. The instant an observer crosses the event horizon, their presence reshapes what exists. This might explain why scientists have never been able to produce a complete map of a black hole's interior. The reason could be simple yet profound. There is no single map to make. Each passage into a black hole creates a different story, depending on the path taken, the interactions made, and the things noticed along the way. The interior is not a fixed place. It is a living process woven together by quantum relationships. Even time itself could be part of this shifting process. From the outside, black holes appear almost frozen in time, like eternal statues. But from the inside, time still flows, though not in the straight, familiar way we know. The flow of time could be guided by observation, directed towards certain outcomes depending on what is being noticed and in what order. Events might not follow a single universal sequence. Instead, the timeline could bend to match the act of observing. This raises unsettling questions. Is there such a thing as an unobserved reality inside a black hole? Does anything exist before it is measured? And if the observer effect plays a role on such a grand scale, could it also be shaping the universe itself? Perhaps our universe too is being continuously sculpted by the observers within it. If so, then the universe is not a rigid mechanical machine but something more alive, something responsive, flexible and ever-changing, moulded by the way we interact with it. Black holes, in this view, are not dead cosmic graveyards, but rather the most dramatic theatres where this process reveals itself. They are places where reality emerges moment by moment, where being and seeing are inseparable. But if our universe itself lies inside a black hole, as some theories suggest, then a new question arises. What lies outside? When we imagine our entire cosmos as a bubble, we naturally wonder what surrounds that bubble. What greater reality gave birth to our own? If everything we know began as the collapse of some massive star in a larger universe, then that parent universe must have had its own stars, its own galaxies, its own gravitational pull, and its own set of physical laws. One of those stars could have collapsed into a black hole so powerful that it gave rise to an entirely new universe on the other side. To an observer in that parent universe, the black hole might look ordinary, dark, dense and silent, perhaps glowing faintly as it leaked out slow trickles of Hawking radiation. But on the inside, a whole cosmos could be blooming. Galaxies could be forming, stars could be igniting, and life could be evolving. From within, billions of years might pass, while from the outside, only the blink of a cosmic eye goes by. Time itself might flow at utterly different rates between the parent and the child. This makes the parent universe even more mysterious. Is it still out there? Did it keep evolving after our universe was born? Or did it vanish the moment its great black hole created us? If our universe is still expanding, that means the energy fueling our expansion has not yet run out. But it does not tell us anything about what happened on the other side of the event horizon. The parent universe might look entirely alien compared to ours, or it could be strangely similar. Some thinkers suggest that child universes inherit traits from their parents. The spin, mass, or charge of the black hole in the parent universe might leave its fingerprint on the child. A rotating black hole could set its universe spinning. The amount of matter swallowed might determine how much energy the new universe begins with. In this sense, each universe could be a kind of child shaped by the black hole that gave birth to it, while still growing and evolving in its own way. But that also means the parent universe might have been dramatically different from our own. Perhaps it allowed for kinds of matter we cannot imagine. Maybe its stars were much larger, or black holes formed more easily. Perhaps its laws of physics were ones we would not even recognize. Our universe feels natural to us, but to an outsider from another cosmos, it might seem odd, unstable, or rare. Is our universe truly unique? If the parent universe contained countless stars, and many of those collapsed into black holes, then it may have seeded countless child universes. Ours could be only one among billions, each born from a different black hole, each unfolding in its own way. The parent universe could be like a vast cosmic nursery, constantly giving birth to new realities. Some imagine that parent universe as unimaginably vast, filled with exotic structures and perhaps even forms of life beyond our comprehension. Others suggest it may already be gone, collapsed long ago, leaving only its children behind. In that case, our universe is like a fossil, the only trace of a greater cosmic event, now drifting on its own through its private time. And since our own universe contains black holes too, we may be parents already. Perhaps even now, new universes are sprouting from the black holes we see in our night sky. This creates a cosmic family tree stretching endlessly. Ancestors, descendants, and generations of universes each linked through black holes. Not infinite in space, but infinite in space-times, each a self-contained reality. If this picture is correct, then the outside of our universe is not a blank void or some empty dimension. It is another universe entirely with its own galaxies, black holes, and history. That universe might itself be inside another, and so on without end. But this raises a final dizzying question. Is there a largest possible outside, an ultimate container holding all of these layers? Or does the nesting of universes continue forever upward, just as it may continue forever downward, with no top and no bottom? We may never know. Our instruments, our telescopes, and even the physical laws we can study are shaped by this universe alone. We cannot step outside to check. All we can do is follow mathematics, build models, and let our imagination explore the possibilities. And yet, there are hints. Some researchers believe that the strange behavior of dark energy, the force pushing our universe to expand faster and faster, might point to something beyond. Perhaps it is pressure leaking in from the outside or a trace of the boundary between universes. When we look at the cosmic microwave background CMB, we mostly see what we would expect if the universe really is flat, infinite, and born from a great explosion known as the Big Bang. Yet, hidden in that ancient light are some peculiar marks that do not quite fit the story. Among the strangest is what scientists call the cold spot. This is a region of the southern sky that looks noticeably cooler than the glowing mist around it. Instead of blending in with its neighbours, this patch seems to stand out like a bruise on the smooth skin of the cosmos. And the cold spot is not the only mystery. The CMB also shows alignments, large-scale patterns that seem to point in particular directions, when in a perfectly uniform universe they should be scattered randomly. If the cosmos were truly isotropic, meaning the same in every direction, we should not see such order. At first, many researchers believed these odd features were simply mistakes, glitches caused by the instruments that detected the light, or interference from dust clouds within our own galaxy. But over time, these excuses began to fade. Careful checks confirmed that the anomalies were real. They have survived decades of scrutiny. While they cannot by themselves prove a new theory of the universe, they continue to whisper that something deeper may be at play. Could these strange marks be telling us about the very shape of the universe itself? Imagine for a moment that our universe was born inside the interior of a curved black hole. The geometry of such a place would not be flat and endless but distorted, like a funhouse mirror bending light. That bending could leave its fingerprints on the CMB. In a flat universe, light rays travel forever in straight lines. But in a curved universe, especially one with intense gravity, such as the inside of a black hole, light can twist, bend, or even loop back on itself. This could paint unusual temperature patterns across the sky. For instance, if the universe were shaped like a three-dimensional sphere, or even like a donut-shaped torus, a single photon travelling in one direction might eventually return from the opposite side, creating repeating patterns in the CMB. If the universe had a negative curvature, like a saddle, it would exaggerate fluctuations on the larger scales. A positive curvature, like that of a hypersphere, would instead smooth out those variations. Interestingly, some of the actual anomalies in the CMB look as though the larger scale fluctuations are suppressed, perhaps a hint that the universe is closed and finite, just as it might be inside a black hole. The cold spot itself remains one of the great puzzles. It stretches roughly 5 degrees across the sky, appearing much colder than nearby regions. One explanation is that it formed because photons, on their way to us, pass through a vast empty region of space known as a supervoid. As they crossed the emptiness, they would have lost energy, arriving cooler than expected. But there is debate over this idea. Are the known voids in that direction truly large enough to cause such a dramatic dip in temperature? If not, then perhaps the cold spot is more than a cosmic coincidence. It could be a direct clue to the curvature of space, or even a leftover mark from the very birth of the universe itself. Another mystery has earned the playful but ominous nickname, the Axis of Evil. This refers to the strange discovery that some of the largest fluctuations in the CMB seem to line up along a single direction in the sky. In a random, uniform universe, such alignments should not exist. Yet they do, and they have been confirmed by multiple satellites, including the Wilkinson Microwave Anisotropy Probe and the Planck mission. Some scientists think this alignment may be nothing more than a statistical fluke. Others, however, wonder whether it signals something profound, that the universe might have a preferred direction, or that its geometry is more complex than we imagined. If our universe was born from a rotating black hole with spin, its original angular momentum could have left behind a scar in the very fabric of space. That scar could still be visible today as a preferred axis. The axis of evil might be nothing less than the fossil trace of that ancient spin, preserved since the moment our universe was born. Clues may also be hidden in the polarization of the CMB. Polarization describes the way light waves are oriented, and it can reveal subtle details about how matter moved and how space was shaped in the infant universe. The Planck satellite and other observatories have mapped this polarization with extraordinary care. The data is messy and complicated, but within it lie patterns, twists and swirls that do not perfectly match the simplest models. These could be signs that our universe carries an inner structure, perhaps born from a space that was already curved or already spinning before the Big Bang. Then comes the question of boundaries. If the universe is finite, does it end somewhere? The standard scientific answer is no. A finite universe could still be unbounded, much like the surface of a sphere, which is closed but endless if you keep walking. Yet if our universe exists inside a black hole, maybe there is indeed a special kind of boundary, a built-in limit to space itself. Such a boundary could bend light paths in strange ways, smooth out or distort the primordial fluctuations, and perhaps even create ring-like patterns in the CMB through a sort of cosmic lensing effect. These patterns would be extremely subtle, easily lost in the noise of measurements, but future telescopes may be sharp enough to find them. Experiments like the Simons Observatory, CMBS-4, and upcoming space missions are being designed to examine the CMB with finer precision than ever before. If space is curved or twisted in a hidden way, these experiments may be the ones to reveal it. The CMB is both a treasure chest and a maze. It is full of information, but also full of noise. Separating the true signals from the clutter is one of the hardest tasks in science. Still, every new observation adds another piece to the cosmic puzzle, and the anomalies remain, refusing to be explained away. If we are truly living inside a black hole, then the signs may already be glowing faintly in the sky, etched into the oldest light we can see. We just need to learn how to read them. This idea leads us to an even stranger question. Would the laws of physics themselves be different in a black hole universe? Physics as we know it rests on a handful of fundamental numbers: the speed of light, the pull of gravity, the charge of the electron, the mass of the proton. None of these values are explained by our theories. We measure them, but we do not know why they are what they are. If they were only slightly different, stars might not ignite, atoms might not bind, and life as we know it could never exist. It seems as though these constants are finely tuned. But what if every black hole creates its own universe, and each new universe rolls the dice again on those constants? Some might turn out similar to ours, others could be utterly alien. Imagine a universe where gravity is stronger. Stars would form quickly and burn themselves out in brief violent flashes. In another, where forces are weaker, matter might hardly clump at all, leaving only thin, ghostly clouds. Some universes might lack stable atoms entirely. Others might never form structures larger than grains of dust. Most would fail before they truly began. Yet a few might survive, finding just the right balance to grow complexity, and perhaps even life. This idea has been called cosmological natural selection. In this picture, black holes act almost like parents, passing traits onto their offspring universes. Not because black holes are special in themselves, but because they reproduce. The universes most likely to survive are those whose laws favour the birth of more black holes. And so, across a vast cosmic family tree, certain traits echo again and again.